Have you ever found yourself gazing up at the night sky, completely mesmerized by the countless stars scattered across the vast expanse above? That feeling of awe, of being a small part of something infinitely grand, is something we all share, a reminder that we're living on a tiny planet, orbiting an ordinary star, somewhere in a universe so immense it's almost beyond comprehension. And yet, as we look deeper into that cosmic darkness, we begin to uncover things that defy logic, things that challenge everything we thought we knew. What if I told you that out there, hidden among the galaxies and nebulas, are objects and phenomena so strange, so utterly bizarre, they seem to belong more to science fiction than to reality? Welcome to a journey into the unknown as we explore the 30 strangest things ever found in the universe. From stars that shouldn't exist to mysterious signals echoing across billions of light years, the cosmos is filled with wonders that stretch the limits of our imagination. Think about it, we're living in an era where every new discovery seems to raise more questions than it answers, where the more we learn, the more we realize how little we truly understand. This isn't just a list of oddities, it's an invitation to step into a world of cosmic mysteries, where the rules of physics are bent, rewritten, or sometimes completely ignored. So get comfortable, open your mind, and let's embark on this adventure together. We'll travel from the familiar sights of our own solar system to the farthest reaches of space, uncovering anomalies that have left even the brightest scientists utterly baffled. This is more than just a countdown, it's a glimpse into the sheer weirdness and wonder of existence itself. Whether you're a seasoned space enthusiast or simply curious about the universe's best-kept secrets, there's something here that will leave you spellbound. Are you ready to discover what lies beyond the stars? Our journey begins not with a dazzling object or a brilliant burst of energy, but with a profound and unsettling emptiness. Nestled within the constellation of Boötes, the herdsman, lies a region of space so overwhelmingly barren that astronomers have nicknamed it the Great Nothing, or more formally, the Boötes Void. Discovered in the 1980s during a galaxy redshift survey, this colossal spherical region stretches an almost incomprehensible 330 million light-years across. To truly grasp that scale, consider this. If you placed our Milky Way galaxy at one edge of this void, you would have to travel through nothingness for hundreds of millions of years at the speed of light before you encountered another island of stars. It is a staggering expanse of near-total darkness, in a universe we generally perceive as being uniformly filled with galaxies. The existence of such a void was a direct challenge to the cosmological principle, which suggests that on a large enough scale, the cosmos should look roughly the same everywhere. The Boötes Void is the exception that threatens the rule. While it's not completely empty, painstaking surveys have identified around 60 galaxies drifting in this vast cosmic desert. That number is shockingly low. A typical region of space of the same volume should contain thousands of galaxies. Finding so few was like discovering an ocean that's almost entirely water, except for one area the size of a continent that is somehow just dry. So how does such a nothingness come to be? Astrophysicists have proposed several theories, the leading one suggesting it is the result of smaller voids merging together over billions of years. Imagine soap bubbles in a sink slowly coalescing into one gigantic bubble. The galaxies we see inside might be the lonely remnants left behind after this epic consolidation. Other, more speculative ideas have been floated, including the wild concept that it could be the imprint of an unimaginably advanced civilization that has somehow harnessed the energy of entire galaxies. While that's a thrilling thought for science fiction, the merging voids theory remains the most scientifically grounded explanation, even if it doesn't fully account for the void's sheer, mind-boggling size. Visualizing the Boötes Void is key to understanding its eerie significance. Picture a map of the observable universe, a glittering web of light where filaments of galaxies cluster together, forming a cosmic structure often compared to a sponge or a neural network. And then, right there in the tapestry, is a gaping spherical hole. Animated comparisons are essential, showing the dense, vibrant neighborhood of our local supercluster, buzzing with galactic activity, and then panning out to reveal this terrifyingly empty pocket of space, a monument to absence that forces us to question the very fabric of our reality. If the Boötes Void feels like a staggering absence, our next discovery is the exact opposite. A presence so bizarre and unexpected that astronomers didn't even have a category for it. In 2019, astronomers using the Australian Square Kilometre Array Pathfinder, or ASCAP, radio telescope were mapping the night sky when they stumbled upon something utterly perplexing. They found strange, ghostly circles of radio light, so peculiar that the researchers simply named them odd radio circles, or ORC. These aren't just faint smudges, they are enormous, distinct rings, and the most baffling part is that they are completely invisible in optical, infrared, or X-ray light. They exist only in the radio part of the electromagnetic spectrum, appearing as vast cosmic halos. The scale of a single ORC is almost impossible to comprehend. Each one spans an incredible million light-years across. To put that into perspective, our entire Milky Way galaxy is a mere 100,000 light-years from end to end. This means a single one of these mysterious circles could comfortably contain dozens of entire galaxies within its diameter. Initially, some scientists thought they might be the remnants of a supernova explosion, or perhaps a familiar ring-like galaxy seen from an unusual angle. But every conventional explanation fell short. They didn't match the profile of any known object, leaving researchers with a genuine cosmic puzzle on their hands. This discovery sent astronomers scrambling for answers, leading to a number of compelling theories. One leading idea suggests that ORCs could be the colossal shockwave from a tremendously powerful event, like the merger of two supermassive black holes. Such a cataclysmic event would unleash an unimaginable amount of energy, creating a spherical shockwave that expands outward for millions of years. Another hypothesis points to a phenomenon known as a starburst wind, where a galaxy experiences a ferocious wave of star formation, blowing a gigantic bubble of energetic particles into the intergalactic medium. Yet some of the more exotic theories are even more fascinating. Could these circles be the throats of hypothetical wormholes predicted by Einstein's equations but never observed? Or perhaps they are the immense signatures of powerful jet bursts from active galactic nuclei, seen head-on as perfect rings. The truth is, no single theory perfectly fits all the data, and it's entirely possible that ORCs represent a type of astrophysical phenomenon we have never witnessed before. Visualizing these objects is key to understanding their mystery. Picture an animated view of a swirling galaxy, and then see a perfect, shimmering ring of energy suddenly bloom around it, expanding to a size that dwarfs everything else in the cosmic neighborhood, a silent, invisible titan revealed only by our most advanced radio eyes. But from the invisible and the enormous, we now turn to a single, specific star that captivated the world and challenged our very understanding of what might be possible around other suns. This is the story of KIC 8462852, a star you likely know by its more popular and far more intriguing name, Tabby's star, or the alien Megastructure star. Located about 1,500 light-years away in the constellation Cygnus, this otherwise ordinary star became the center of one of the biggest astronomical mysteries of the last decade, all because of the way its light flickered. The discovery was made by NASA's Kepler Space Telescope, a mission designed to find planets by watching for the telltale periodic dimming that occurs when an orbiting world passes in front of its host star. These dips are usually tiny, predictable, and repeat like clockwork, but Tabby's star was different. Citizen scientists participating in the Planet Hunters project, who were examining Kepler's public data, flagged this star as deeply anomalous. Its light curves showed not the gentle, symmetrical dips of a planet, but wild, irregular, and dramatic plunges in brightness. We're talking drops of up to 22%, a staggering amount. For comparison, a Jupiter-sized planet transiting a Sun-like star would cause a dimming of only about 1%. This was something else entirely. Something massive was blocking the light, and it wasn't doing so with any recognizable rhythm. The strangeness didn't end there. Long-term studies of the star's historical data revealed another baffling layer. Tabby's star appears to have been gradually dimming over the past century. While this finding has been debated, it added fuel to the fire of a mystery that already seemed to defy all conventional explanations. The internet, of course, immediately lit up with the most exciting possibility. Could this be evidence of an alien megastructure, specifically a Dyson sphere or Dyson swarm, a hypothetical array of energy-collecting satellites built by an advanced civilization to enclose their star and harness its entire power output? The irregular, blocky dips could be explained by vast swarms of constructed objects passing in front of the star, their uneven shapes and orbits creating the bizarre, aperiodic dimming patterns. It was a concept straight out of science fiction, and for a while it was a legitimate topic of scientific discussion. Naturally, astronomers began rigorously hunting for more plausible natural causes. The leading theory for some time involved a giant, fragmented swarm of comets, stirred up by the gravitational influence of a nearby star, creating a vast cloud of dust and debris that could intermittently obscure our view. More recent studies, incorporating data from the Spitzer and Swift telescopes, point strongly towards uneven clouds of interstellar dust. Different types of dust block different wavelengths of light in specific ways, and the observations suggest that fine, microscopic dust particles are the primary culprit, causing the deep dimming in a way that solid, opaque objects like planet fragments or megastructures would not. Yet the dust explanation isn't entirely perfect, and some peculiarities remain. This ongoing ambiguity is perhaps the star's greatest legacy. It demonstrated the powerful role of citizen science in modern astronomy and reinvigorated public interest in the search for extraterrestrial intelligence. It showed that even in a vast sea of data, human curiosity and pattern recognition can spot the one thing that doesn't fit, opening a door to a wonderful, multi-year scientific detective story. To visualize this, imagine an animation showing a star's steady light. Then see huge, jagged shapes completely unlike the smooth curve of a planet lumbering across its face, causing the light to plummet erratically. A sequence so strange it made us all wonder, if just for a moment, if we were seeing the shadows of something truly otherworldly. Leaving behind the mysterious depths of interstellar space, we arrive at a wonder much closer to home, yet no less astounding. For our next strange thing, we travel to the sixth planet from the Sun, the ringed jewel of our solar system, Saturn. While its breathtaking rings are its most famous feature, a far more peculiar and persistent mystery swirls at its north pole. There, dominating the atmosphere, is a perfect gargantuan hexagon. This is not a feature from a sci-fi movie or a digital glitch. It is a real six-sided jet stream, a geometric atmospheric phenomenon that has defied easy explanation for decades. This bizarre structure was first glimpsed by the Voyager spacecraft in the 1980s, but it was NASA Cassini mission that provided the stunning, high-resolution data that truly captivated scientists and the public alike. The numbers involved are staggering. Each side of the hexagon is longer than the diameter of Earth. The entire structure is so vast that 4 of our planets could be lined up side by side and still fit comfortably within its boundaries. And unlike the ever-changing weather patterns on our own world, this colossal hexagon is incredibly stable. It has been spinning at Saturn's north pole, unceasing and seemingly unchanging for at least 40 years and likely much longer. It is a permanent feature etched into the atmosphere of a gas giant. So how does a planet governed by the same laws of physics as Earth produce such a perfect and persistent geometric shape? The leading theory points to a fascinating interplay of physics. Scientists believe it is a manifestation of a standing wave pattern, a kind of stable atmospheric oscillation. Imagine water swirling in a sink as it drains, creating a small, temporary vortex. Now amplify that process to a planetary scale. Deep within Saturn, currents of gas moving at different speeds could create these giant, stable patterns. The planet's rapid rotation a day on Saturn is only about 10.5 hours long, likely acts like a mold, shaping this turbulent fluid dynamics into a six-sided form instead of a more common circular vortex. What makes the hexagon even more mesmerizing is its intricate internal structure. Cassini's imagery revealed that within the jet stream, the hexagon acts like a containing wall for weather systems. Inside its boundaries, smaller storms spin and dance like moons orbiting a planet, but they are never able to break through the hexagonal barrier. The central region even features a massive, swirling hurricane with an eye so large it could swallow our planet whole. This entire system is a self-contained meteorological marvel, a clockwork mechanism of wind and cloud operating on a scale we can barely imagine. Visualizing the hexagon is key to appreciating its sublime weirdness. Picture a breathtaking time lapse from Cassini, showing the hexagon rotating majestically, its honeycomb-like walls sharp and clear against the swirling golden haze of Saturn's atmosphere. The contrast with our own planet's chaotic and transient weather systems could not be more pronounced. Our hurricanes form and dissipate in days. Saturn's North Pole hexagon is a monument to stability, a testament to the strange and beautiful physics that can emerge when nature operates on a grand planetary scale. It serves as a powerful reminder that even within our own cosmic neighborhood, there are worlds that hold secrets far beyond our everyday experience. After witnessing the enduring geometric perfection of Saturn's hexagon, we now turn from a visible planetary scale mystery to one that is heard, not seen, a fleeting whisper from the depths of space that lasted for just 72 seconds, yet has echoed through the decades as perhaps the most tantalizing hint that we might not be alone. This is the story of the WOW signal, a burst of radio waves that arrived in 1977 and remains, to this day, the most compelling candidate for a potential alien transmission ever detected. The event took place on the night of August 15th at Ohio State University's Big Ear Radio Telescope. This massive instrument was methodically scanning the sky, one narrow strip at a time, as part of the ongoing search for extraterrestrial intelligence, or SETI. The system was automated. Its computer would print out strings of alphanumeric characters representing signal strength, and typically, the readout was a monotonous sequence of noise and background static. But on this night, volunteer researcher Jerry Amon was reviewing the previous night's data when his eye caught a sequence of characters so extraordinary that he circled it on the printout and simply wrote, "Wow." In the margin, that single emotional annotation gave the signal its famous name. What made this blip so special? It wasn't its duration, but its pristine, artificial-looking profile. The signal was a strong, narrowband radio transmission at exactly 1,420 MHz. This frequency is no random number. It is a protected, quiet band, a radio frequency naturally emitted by hydrogen, the most common element in the universe. The logic is brilliant. Any technologically advanced civilization might logically choose this universal, significant frequency to announce their presence, much like setting up a lighthouse on a well-traveled nautical channel. The signal's intensity rose and then fell over exactly 72 seconds, the precise time it takes for a fixed telescope like the Big Ear to observe a single point in the sky as the Earth rotates. This perfect curve was the fingerprint of a celestial source moving through the telescope's field of view. Every characteristic pointed to an origin far beyond our solar system, and more importantly, beyond any known natural phenomenon. The immediate and most frustrating part of the story is what happened next: nothing. Despite immediate efforts and dozens of subsequent searches over the next 40 years, the signal was never heard again. It was a one-time event, a cosmic shout that vanished into silence. This singular nature is what fuels both the mystery and the skepticism. Could it have been a secret military transmission? A reflected signal from a piece of space debris? Every prosaic explanation has been examined and found wanting. The signal's specific frequency and bandwidth rule out known satellites or aircraft, and its movement across the sky was perfectly consistent with a distant, fixed point in space. For decades, the source of the WOW signal was a complete mystery, a blip from an unknown point in the constellation Sagittarius. However, in 2020, a compelling new theory emerged. Professor Alberto Caballero, while scouring data from the European Space Agency's Gaia mission, identified a potential candidate, a Sun-like star, almost perfectly identical to our own Sun, located in the exact region of the sky from which the signal originated. This star, designated 2M134J014458 plus 0141416, is a tantalizing clue, not proof. It offers a specific, intriguing target for future observations, a place to point our most sensitive arrays and listen intently for another hello. The enduring power of the WOW signal lies in its perfect ambiguity. It was just too perfect to be easily dismissed as noise, yet just too brief to be confirmed as a message. It sits in that thrilling middle ground, a permanent invitation to wonder. It represents the ultimate what if, a moment that captures the essence of the scientific search for other life, a pursuit defined by patience, meticulous observation, and the unwavering hope that one day the silence will be broken again. To visualize it, picture the actual computer printout with its columns of numbers and letters, and that one stunning sequence, 6 equals QU, circled in red, a human moment of awe forever etched onto a page of data, a testament to the idea that the universe might be trying to tell us something. From the isolated mystery of a single, unrepeatable signal, we now zoom out to a cosmic enigma of unimaginable scale, one that suggests the very fabric of our universe might be tugged by forces from outside. This is the mind-bending puzzle known as the dark flow. Discovered in 2008 by a team studying data from NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP, this phenomenon describes a strange, coordinated motion of entire galaxy clusters. It's not the expansion of the universe which pulls galaxies apart, but a peculiar, additional drift, as if these colossal structures are all being pulled in the same specific direction by some invisible cosmic current. The detection method itself is a masterpiece of scientific ingenuity. Researchers weren't looking at the galaxies themselves, but at the echo of the Big Bang, the cosmic microwave background radiation. This faint, cold light fills the entire universe and serves as a perfect backdrop against which to measure motion. As galaxy clusters move through space, the hot gas and dust within them scatter the CMB photons in a specific way, a subtle effect known as the kinematic Sunyaev-Zeldovich effect. By meticulously mapping this distortion across the sky, the team, led by Alexander Kashlinsky, made an astonishing discovery. Hundreds of galaxy clusters, some of them billions of light-years away, were all streaming at tremendous velocities toward a single patch of sky between the constellations of Centaurus and Vela. It was as if someone had found a cosmic river with entire islands of stars caught in its flow. This presented a monumental problem for the standard model of cosmology, which states that on the largest scales, the universe should be homogeneous and isotropic, meaning matter and motion should be evenly distributed in all directions. The gravitational pull from all the matter we can see and the dark matter we can't see should, in theory, account for all large-scale motion. The dark flow suggests something else is at work, a gravitational influence so immense it lies beyond the horizon of our observable universe. The most staggering implication is that this flow could be evidence of other universes. In the multiverse theory, our universe is just one bubble in a vast cosmic foam. The gravitational tug from a neighboring, incredibly massive universe beyond our own could be pulling on the matter within our visible cosmos, creating this mysterious drift. It's a hypothesis that ventures from astrophysics directly into the realm of metaphysics. Naturally, a claim this extraordinary has faced intense scrutiny and skepticism. Some scientists have questioned the statistical significance of the results or proposed that subtle errors in processing the incredibly complex CMB data could have created this apparent flow. Subsequent studies, some using data from the Planck satellite, have both challenged and supported the original findings, keeping the debate very much alive. The central question remains, is the dark flow a real physical phenomenon, or is it an artifact of our measurement? Visualizing this is key. Picture an animated map of the entire observable universe, a sphere with our planet at the center. Now see hundreds of arrows representing galaxy clusters, not pointing outward from the expansion, but all angling in a coordinated stream toward one specific edge of the sphere, hinting at a source of influence from the profound nothingness beyond. It's a visual that challenges our deepest understanding of reality, suggesting that our universe is not an isolated island, but part of a far grander and utterly mysterious cosmic archipelago. Moving from the strange, coordinated drift of entire galaxy clusters, we turn our gaze inward to the very heart of our own cosmic home, only to discover it holds a violent secret of its own. Jutting out from the center of the Milky Way like the hourglass of a titan are two colossal spheres of energy known as the Fermi Bubbles. These are not subtle features. They are a pair of massive gamma-ray emitting structures that extend an astonishing 25,000 light-years above and 25,000 light-years below the galactic plane. To comprehend this scale, imagine our entire galaxy, a disk 100,000 light-years wide. These bubbles stretch for half that distance, from the core straight up and down into the emptiness of the galactic halo. If our eyes could see in high-energy gamma rays, this structure would dominate the night sky, a vast, faint hourglass of light with its waist cinched at the center of the Milky Way. These giants remained hidden from us until just over a decade ago. Their discovery was a triumph of precise, space-based observation. In 2010, scientists analyzing data from NASA's Fermi Gamma-Ray Space Telescope, which is designed to map the universe's highest energy light, noticed something peculiar. There was a persistent, diffuse glow of gamma-ray emission that couldn't be explained by any known source. It wasn't a point of light like a pulsar or a quasar. It was an immense structured haze. After carefully subtracting all the background noise and known gamma-ray contributors, the stunning outline of these two enormous bubbles emerged from the data, a landmark discovery that revealed a previously unknown chapter in our galaxy's history. The immediate and most pressing question was, and still is, what created them? The bubbles are a cosmic fossil, the lingering aftermath of a truly cataclysmic event. The prime suspect sits right at their base, Sagittarius, a star, the supermassive black hole at the very center of our galaxy. While it's relatively quiet today, the Fermi bubbles are strong evidence that it was not always so serene. The leading theory suggests that in the relatively recent past, by cosmic standards, Sagittarius, a star, experienced a period of intense activity. It may have devoured a vast amount of material, perhaps a giant molecular cloud or even a star, in a violent feeding frenzy. This accretion process would have generated unimaginably powerful jets of energy and matter, shooting out from the black hole's poles at nearly the speed of light. These jets would have blown a gigantic bipolar bubble into the diffuse gas that surrounds our galaxy, heating it and filling it with high-energy particles that continue to emit gamma rays millions of years later. An alternative, though not mutually exclusive, theory points to a frenzy of star formation. The galactic center is a crowded, chaotic place, and a sudden burst of millions of stars being born and subsequently dying in supernova explosions could have collectively produced a powerful galactic wind, a supersonic outflow that inflated these massive structures. The truth likely involves a combination of these events, a feedback loop where star formation feeds the black hole and the black hole's outbursts regulate star formation. What is certain is that the Fermi bubbles are a stunning reminder that our galaxy is not a static, peaceful place. It has a dynamic and violent life cycle, with periods of intense activity and upheaval that can shape its structure for eons. Visualizing these bubbles is essential to appreciating their grandeur. An animation would start with a familiar side view of the Milky Way, a glowing disk with a bright central bulge. Then we'd see the bubbles erupt from the core, inflating upward and downward like two colossal balloons, quickly expanding to a size that dwarfs the galactic disk itself. To provide scale, we could see our solar system's location, a tiny speck about 27,000 light-years from the center, placed well within the lower reaches of the southern bubble, living in the faint, glowing aftermath of a galactic explosion that occurred long before our sun even existed. But from the vast, energetic structures within our own galaxy, we now focus on a single, exquisite cosmic object that stands out not for its power, but for its impossible, almost artificial geometry. Drifting through space some 2,300 light-years from Earth, in the constellation Monoceros, is a nebula so uniquely structured that it seems to defy the normally chaotic rules of cosmic formation. This is the Red Rectangle Nebula, a profound mystery wrapped in a stunning, blood-red hue and a shape so precise it looks as if it were crafted by a celestial architect. The nebula's name is a slight misnomer. It isn't a perfect rectangle, but rather what astronomers describe as a biconical or X-shaped structure. At its heart lies a binary star system, two stars locked in a tight 15.6-month orbital dance. The primary star is a post-asymptotic giant branch star, a sun-like star in its final death throes, having exhausted its nuclear fuel and now in the process of shedding its outer layers into space. It is this dying star that provides the raw material for the nebula. Its companion, a smaller white dwarf star, plays the crucial role of sculptor, as the dying primary star expels its gas and dust in a spherical outflow. The gravitational influence and accretion disk of its dense white dwarf partner funnel this material into two opposing cones or jets. Because we view this system almost directly from the side, these two cones create the dramatic illusion of a rectangle with a central X, a structure so sharp and defined it's unlike any other nebula we've ever observed. Yet the geometry gets even stranger. High-resolution images from the Hubble Space Telescope reveal the nebula's most captivating feature, a series of perfectly spaced horizontal rungs, like the rungs of a ladder or the grooves on a vinyl record connecting the two sides of the X. These are not static features, they are a historical record of the system's pulsing heart. Astronomers believe they are created by episodic outbursts from the central binary system. Every few hundred years, the interaction between the two stars, likely involving mass transfer from the dying star to the white dwarf, triggers a new eruption of material. This new outflow expands until it collides with the slower-moving ejector from previous eruptions, creating a shock wave that lights up as a distinct, equidistant rung. The result is a cosmic timeline, a breathtakingly regular series of waves frozen in space, each marking a violent event in the life of this dying stellar pair. The intense red color, which gives the nebula its name, is another piece of the puzzle. This deep crimson glow comes from a specific type of organic molecule known as polycyclic aromatic hydrocarbons, or PAH. These are complex carbon-based compounds that fluoresce or light up when bombarded by the intense ultraviolet radiation from the hot central stars. The presence of these molecules is fascinating, as they are considered some of the basic building blocks of life. In the harsh environment of this nebula, we are essentially witnessing the large-scale production of these probiotic materials, which will one day be ejected into the interstellar medium to perhaps one day become part of new planetary systems. The red rectangle is not just a beautiful tombstone for a dying star, it is a factory for the very ingredients of life. Visualizing this object is key to appreciating its sublime weirdness. Hubble's imagery is nothing short of spectacular, showing a glowing ruby-red frame with shockingly sharp, dark-laced rungs cutting across it. To truly understand its formation, an animated model is essential. We'd start with the central binary stars, then see the spherical outflow get pinched and shaped by the companion star's disk into two opposing jets. Then, a pulse of energy would erupt from the center, creating a new shell of material that expands outward until it forms the next bright rung in the sequence, building the cosmic ladder step by step over millennia. This nebula is a perfect, natural example of how the simple, chaotic laws of physics can, under very specific conditions, produce structures of breathtaking symmetry and order. A reminder that the universe is capable of creating art on a scale we are only beginning to appreciate. And now we arrive at a star that pushes the boundaries of what we consider a natural object, inviting us to seriously contemplate the possibility of technology on a scale so vast it harnesses the power of an entire sun. This is the compelling case of TYC 6111-11621, a seemingly ordinary star that became the subject of intense speculation after it was found to be emitting a bizarre and powerful infrared signature, a clue that some believed might point to the existence of a theoretical alien megastructure known as a Dyson sphere. The discovery, fittingly, once again came from the sharp eyes of citizen scientists, poring over publicly available data from NAS, a Wide-Field Infrared Survey Explorer, or WISE telescope. Volunteers with the Planet Hunters project weren't looking for planets this time. They were searching for stars that displayed an unusual excess of infrared radiation. Their target was a specific type of object, but what they found in this star was something else entirely. The data showed that TYC 6111-1162-1 was radiating an enormous amount of infrared heat, far more than could be explained by the star itself. It was as if the star was being shrouded by something with a very large surface area, something that was absorbing the star's visible light and re-radiating it back out as waste heat in the infrared part of the spectrum. This is precisely the signature that astrophysicist Freeman Dyson theorized back in 1960. He proposed that a sufficiently advanced civilization, having exhausted the energy resources of its home planet, might eventually seek to capture the entire energy output of its parent star. They would construct a vast swarm of energy-collecting satellites or panels, eventually encircling the star in a shell or a loose constellation, a Dyson sphere. Such a structure would be invisible in optical light, but would glow brightly in infrared due to the heat generated by its energy conversion processes. The data from this star was on paper a near-perfect match for this hypothetical signature. The potential implications were staggering, suggesting we might have stumbled upon evidence of a Kardashev Type II civilization, one that commands the power of its entire star system. Of course, extraordinary claims require extraordinary evidence, and astronomers immediately began searching for more conventional, natural explanations. The primary and most plausible theory involves a massive circumstellar disk. This wouldn't be a clean, protoplanetary disk of pristine gas and dust, but rather a thick, dusty debris field, perhaps the chaotic aftermath of a colossal planetary collision. Imagine two Earth-sized planets, or even larger, smashing into each other. Such a catastrophic event would pulverize the worlds into a cloud of fine dust and molten rock, creating a gigantic, hot ring of debris that would encircle the star. This dust would absorb the star's light and re-radiate it as infrared, creating a signal very similar to what was observed. Other possibilities include a rare and thick ring of dust and asteroids, or even a circumstellar disk being viewed from an unusual, edge-on angle that maximizes its obscuring effect. The true scientific value of this discovery lies not in proving the existence of aliens, but in demonstrating a powerful new methodology for SETI, the search for extraterrestrial intelligence. Instead of listening for deliberate radio signals which an advanced civilization might not be broadcasting, we can now search for unintentional technosignatures, the large-scale industrial byproducts of an advanced society, like the waste heat from a Dyson swarm. This star and others like it catalogued in studies such as the Galileo project serve as perfect test cases. They are natural laboratories for refining our models and learning to better distinguish between the oddities of astrophysics and the potential fingerprints of technology. It represents a shift from passive listening to active, forensic astronomy, sifting through the light of distant suns for clues of cosmic construction projects. Visualizing this is key to understanding the profound mystery. An animation would show the star first as a normal point of light. Then, we'd see the infrared data overlay as a massive, glowing heat haze surrounding it, a signature of something massive and warm that our eyes cannot see. We could then compare two possibilities side by side, one showing a chaotic cloud of dust and rock, the remnants of a violent planetary accident, and the other showing an intricate, geometric swarm of manufactured panels, slowly orbiting the star in a precise, organized ballet. This star remains an enigma, a powerful reminder that as our tools for observing the universe improve, we will inevitably find more things that don't fit our existing categories, objects that live in the thrilling gray area between natural wonder and artificial artifact. Leaving behind the theoretical signatures of cosmic construction, we plunge into a world of the utterly minuscule, into the realm of particles so elusive they can pass through light years of solid lead without a single interaction. These are neutrinos, often called ghost particles, and while their existence is a cornerstone of modern physics, some of their recent high-energy arrivals on Earth point to cosmic events of such staggering violence that they defy our complete understanding. To grasp why neutrinos are so ghostly, you have to understand their nature. They are fundamental particles, incredibly tiny, with almost no mass and, crucially, no electrical charge. This means they are immune to the electromagnetic forces that govern most interactions in the universe. They don't reflect light, they don't repel or attract other matter. They are the ultimate cosmic spectators, barely engaging with the universe at all. Trillions of them are passing through your body every second, coming from the sun, from distant supernova, and from the Big Bang itself, completely unnoticed. Catching one is like trying to trap a beam of light with a net. It requires a detector of immense size and cleverness. That detector is the Ice Cube Neutrino Observatory, a project of breathtaking scale and ingenuity buried deep in the Antarctic ice at the South Pole. It isn't a traditional telescope, it's a cubic kilometer of pristine, ancient ice, instrumented with over 5,000 ultra-sensitive optical sensors strung along 86 cables buried more than a mile deep. These sensors don't look for the neutrinos themselves, but for the faint, ethereal blue glow of Cherenkov radiation, a shockwave of light produced when a neutrino, against all odds, actually collides with an atom in the ice. That incredibly rare collision creates a secondary particle, like a muon, that travels faster than the speed of light in that medium, generating a faint blue streak that the sensors can pick up. By analyzing the timing and pattern of this light, scientists can trace the particle's path back to its origin in the sky, turning a massive block of ice into the world's largest and strangest particle detector. The holy grail of this endeavor is to catch high-energy neutrinos, those that have been accelerated to nearly the speed of light by the most powerful engines in the universe, supermassive black holes merging neutron stars or supernova remnants. These neutrinos are cosmic messengers carrying information directly from the heart of these cataclysmic events, information that isn't scrambled by magnetic fields like charged particles are. When we detect one and can trace its path back to a known object, it's a monumental success, a direct telegram from a cosmic catastrophe. But sometimes the message is confusing. In September 2017, the IceCube detector picked up a single, incredibly high-energy neutrino. This event was so significant that it triggered an automatic alert to observatories around the world. Astronomers swung their telescopes to the source direction and found something spectacular, a blazingly bright flare from a blazar 4 billion light-years away, a galaxy powered by a supermassive black hole shooting a jet of radiation directly at Earth. It was a perfect match, a triumph of multi-messenger astronomy. However, not all events have such a clear return address. IceCube constantly detects high-energy neutrinos that simply cannot be pinned to any known source. They arrive from seemingly empty patches of space, with no accompanying flash of gamma rays or light that our other telescopes can see. These are the true ghost events. They tell us that a cataclysm of immense proportions happened somewhere, but it was either too far, too obscured by dust, or of a type that doesn't produce the traditional electromagnetic signals we know how to look for. They are the silent alarms from cosmic crimes unseen, hinting at entire classes of extreme astrophysical phenomena that we have not yet discovered or understood. Visualizing this is key to appreciating the mystery. Imagine an animation starting from the perspective of the neutrino itself, flying unimpeded through stars, nebulae, and entire galaxies for millions of years. Then it strikes a single atom in the deep Antarctic ice, and for one fleeting moment it betrays its existence with a faint, expanding sphere of blue light, a flash in the deepest dark that signals of violence occurring in a galaxy far, far away. The real magic happens when we see that path traced backward, shooting out of the ice and across the solar system, only to dead end in a vast, empty void between the constellations, a question mark hanging in the blackness. These ghost particles are our only clues that the universe is hiding its most furious secrets in the darkest of corners. But what if I told you that right now, as you watch this, a silent hurricane is blowing through our solar system and you're standing directly in its path? This isn't a storm of wind or rain, but something far more strange and imperceptible, a hurricane of dark matter. Known formally as the S1 stream, this cosmic event is a vast, high-speed river of this mysterious substance, and it's currently washing over Earth, offering scientists an unprecedented opportunity to finally detect the elusive material that makes up the vast majority of matter in our universe. The story of this dark matter hurricane begins billions of years ago with an act of cosmic cannibalism. Our Milky Way galaxy, like all large galaxies, grew to its current size by consuming smaller dwarf galaxies that ventured too close. The S1 stream is the ghostly remnant of one such meal. It is the shredded, tidal tail of a small dwarf galaxy that was torn apart by our galaxy's immense gravity long ago. The stars from that devoured galaxy were stretched into a long, coherent stream that continues to orbit the Milky Way center. But crucially, where there are stars, there is an even greater amount of dark matter, the invisible gravitational scaffolding that holds galaxies together. So this stream isn't just made of the visible stars we can track. It is primarily composed of a dense, fast-moving flow of dark matter particles, all moving together in the same direction at roughly 500 kilometers per second. This is where the phenomenon becomes incredibly relevant to us. Precise data from the European Space Agency's Gaia mission, which is mapping the motion of billions of stars, allowed astronomers to pinpoint the trajectory of this S1 stream. They made a stunning discovery. This stream is passing directly through our region of the solar system. We are quite literally in the midst of a dark matter wind. For scientists trying to detect dark matter, this is a potential game changer. Most experiments are built on the assumption that dark matter particles are moving in a relatively calm, isotropic halo around our galaxy. Detecting them is like trying to hear a whisper in a crowded room, but the S1 stream changes that. It provides a dense directional source. Instead of listening for random whispers from all directions, detectors could now know exactly where to point their ears, tuning in to a specific direction where the signal should be significantly stronger. So how do you catch a ghost? The leading method involves incredibly sensitive detectors located deep underground, in abandoned mines or beneath mountains, where they are shielded from the cacophony of cosmic rays and other background radiation. These experiments, with names like LUX Zeppelin and Xeno NNT, use massive vats of ultra-pure liquid xenon. The idea is that a dark matter particle, known as a WIMP, weakly interacting massive particle, might, on an incredibly rare occasion, bump into the nucleus of a xenon atom. That tiny collision would produce a faint flash of light and a free electron, both of which can be detected by sensitive photomultiplier tubes lining the tank. It's a needle in a haystack search, but the S1 Hurricane offers a much denser haystack to sift through, and it tells us exactly which direction the needle might be coming from. Visualizing this invisible storm is key to understanding its profound implications. An animation would start by showing the Milky Way, then zooming in on the long, ribbon-like stream of stars that is the visible tracer of S1. Then we'd see that ribbon is filled with a vastly more numerous cloud of invisible particles, represented perhaps by a subtle, shimmering effect. The camera would then zoom all the way to our solar system, showing this dense cloud sweeping through the planets, passing through the Sun, and enveloping the Earth. We could even see an illustration of a deep underground detector, with a single, rare interaction from the stream causing a pinpoint of light to flash in the darkness. This isn't just a distant curiosity, it's a real-time cosmic event that could finally lift the veil on the universe's deepest secret, proving that even the most enigmatic forces in the cosmos can leave a trace for those who know how to look. Yet for all the secrets we're uncovering within our own galaxy, there is a far greater, unseen force pulling not just us, but our entire galactic neighborhood on a breathtaking journey through the cosmos. This brings us to one of the most profound and long-standing mysteries in modern astronomy, the Great Attractor. It is a gravitational anomaly of such immense power that it is pulling our entire local group of galaxies, including the Milky Way, toward it at a staggering speed of over 600 kilometers per second. We are caught in a cosmic current, moving toward a point in space we cannot even see. The discovery of this motion was a gradual process that reshaped our understanding of the universe's large-scale structure. It began with mapping the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation creates a universal frame of reference, a backdrop against which all motion can be measured. When astronomers looked at this map, they found our galaxy is not stationary. It's moving relative to this background. But the real breakthrough came from plotting the velocities of thousands of other galaxies. They all showed a coherent flow, a vast river of galaxies all streaming in the same direction toward a point in the southern sky, centered on the constellations Norma and Centaurus. This wasn't random motion, it was a targeted migration, and something incredibly massive had to be causing it. The central problem, the great frustration for astronomers for decades, was that this mysterious gravitational epicenter lies directly behind the plane of our own Milky Way galaxy, in a region known as the zone of avoidance. This isn't a literal void, it's an area of the sky obscured by the thick gas, dust, and countless stars of the galactic bulge. It's like trying to see a distant mountain range while standing in the middle of a dense, foggy forest. For the longest time, optical telescopes were completely blind to whatever lay in this direction, leaving the nature of the Great Attractor shrouded in mystery and ripe for speculation. The key to piercing this veil came not from visible light, but from infrared and radio astronomy. Instruments like NASA's Spitzer Space Telescope and the Parkes Radio Telescope in Australia can peer through the cosmic dust. Infrared light has longer wavelengths that can pass through obscuring material, while radio waves can be emitted by hydrogen gas, allowing us to map the structures hidden behind the Milky Way's disk. What these tools revealed was astonishing. The Great Attractor isn't a single, unimaginably dense object. Instead, it appears to be the gravitational heart of a colossal supercluster of galaxies, now known as the Laniakea supercluster, a Hawaiian word meaning immense heaven. Laniakea is our true cosmic address. It is a vast filamentary web of over 100,000 galaxies, spanning 500 million light-years. Our own Milky Way is not even in its dense core. We reside on a remote suburban filament on its far outskirts, like a home on the very edge of a sprawling continent. The gravitational pull we feel is the combined might of this entire immense structure, the countless galaxies, and more importantly, the vast reservoirs of dark matter that bind them together, pulling everything within its domain toward its center of mass. Recent observations suggest that the story might be even grander. The pull we feel may not be from Laniakea alone. There is evidence that the Great Attractor itself and our entire supercluster is being pulled toward an even more massive structure billions of light-years away, known as the Shapley supercluster. This creates a cosmic hierarchy of gravity, a tug-of-war on an unimaginable scale where we are drawn toward the Great Attractor, which in turn is drawn toward something else even more immense. Visualizing this journey is essential. An animation would start with a map of the local universe showing our Milky Way as a single point. Then, we'd see the velocity vectors of nearby galaxies, all aligning into a coherent flow like iron filings orienting toward a magnet. The view would then pull back, revealing the beautiful spider web-like structure of the Laniakea supercluster, with all its galactic filaments flowing inward toward the gravitational basin of the Great Attractor, a journey we are all a part of, racing through the void toward a destination hidden in plain sight. From the grand, invisible currents shaping our entire galactic neighborhood, we now turn our attention to a specific, beautiful, and violent cosmic wonder that looks more like a deep-sea creature than a collection of stars. Drifting through the vast ocean of space is JO 206, a galaxy that has earned the nickname space jellyfish for its breathtaking and eerie appearance. In stunning images from telescopes like the Very Large Telescope in Chile, this galaxy presents a luminous central body, or bell, with long, trailing tendrils of glowing gas that stretch outward for hundreds of thousands of light-years, creating an almost biological silhouette against the blackness of space. This mesmerizing form is not the result of a peaceful process, but rather one of extreme violence and pressure. JO 206 exists within a dense galaxy cluster, a crowded metropolitan area of the universe where galaxies zip past one another at tremendous speeds. The space between these galaxies is not empty. It is filled with a superheated, thin plasma known as the intracluster medium. As a spiral galaxy like JO 206 plunges through this searing hot gas at speeds of several million miles per hour, it experiences an effect astronomers call ram pressure stripping. Imagine sticking your hand out of the window of a speeding car. The wind pushing against your palm is a tiny-scale version of this powerful intergalactic phenomenon. For the galaxy, this cosmic headwind is so intense that it acts like a gravitational squeegee, violently stripping away the galaxy's own reservoir of gas and dust, the very raw materials needed to form new stars. This is where the beautiful tentacles are born. The gas that is ripped away from the galaxy's disk doesn't just vanish, it is stretched out into those long, streaming tails. But the process gets even more fascinating. The immense pressure from the intracluster medium doesn't just strip the gas away, it also compresses it. Within these drawn-out tendrils, the gas clouds collapse under their own gravity, igniting a firestorm of new star formation. This means the jellyfish's tentacles are not just trails of death, they are also stellar nurseries glowing with the brilliant blue light of hot, young stars being born in the most hostile of environments. It's a paradoxical scene of creation fueled by destruction. where the very process that is killing the galaxy by robbing it of its future star-making fuel is simultaneously triggering a final, glorious burst of stellar birth. Studying these jellyfish galaxies provides astronomers with a unique and urgent laboratory to understand galactic evolution. For a spiral galaxy, losing its gas is a death sentence. It's the galactic equivalent of having your entire pantry and all your future seeds cleared out. Without gas, the galaxy cannot form new stars. Over billions of years, its existing population of stars will age and redden, and the galaxy will eventually transform from a vibrant, star-forming spiral into a quiet, red and dead elliptical galaxy. Jellyfish galaxies like JO 206 offer us a real-time snapshot of this critical metamorphosis. We are witnessing the quenching of a galaxy, a fundamental transition that shapes the population of galaxies we see in the universe today. The detail within these tendrils is what holds the key. By analyzing the light from the newly formed stars within them, scientists can study the star formation process in an extreme and unusual environment far from the galaxy's main disk. They can measure how efficiently gas is turned into stars under intense pressure, and how the composition of these stars might differ from those formed in more tranquil regions. This helps refine our models of how all stars are born. Furthermore, tracking the motion and composition of the stripped gas reveals how enriched elements, the heavy atoms forged in stellar furnaces, are ejected from galaxies and recycled into the intracluster medium, seeding future generations of stars and planets with the building blocks of life. To truly appreciate this phenomenon, visualizations are essential. We can see a side-by-side comparison, starting with a simulation of a serene spiral galaxy. Then watch as it enters the hot, diffuse gas of a galaxy cluster, seeing the bow shock form at its leading edge and the turbulent wakes of gas being pulled away into long, elegant tails. This is followed by the stunning telescopic imagery itself, the Hubble or VLT photos that reveal the ghostly, blue-hued tendrils, each a blazing trail of young stars marking the galaxy's tragic yet beautiful path of disruption. It's a powerful reminder that the universe is a dynamic and often violent place, where even the most island-like galaxies are not isolated, but are constantly interacting with and being shaped by their environment in the most spectacular ways. While the grand structures of galaxies and clusters shape the cosmos on the largest scales, some of the universe's most intense dramas play out in the intimate confines of a binary star system. Our next discovery is a terrifyingly efficient cosmic predator, a stellar vampire known as the Black Widow pulsar. This isn't just a star, it's a rapidly spinning, city-sized corpse that is methodically devouring its companion, earning its name from the spider that consumes its mate. At the heart of this system lies a pulsar, designated PSRB 1957+20. A pulsar is the ultra-dense, rapidly spinning remnant of a massive star that went supernova. This particular one is a millisecond pulsar whirling around hundreds of times per second, and it's this incredible rotation that powers its deadly nature. The pulsar emits a furious torrent of radiation and particle winds from its magnetic poles, and as it spins, these beams sweep across space like a monstrous cosmic lighthouse. But this pulsar isn't alone. It's locked in a tight, 9-hour orbital dance with a small, low-mass star, its destined victim. The two are so close that the companion star is tidally locked, forever showing one face to its predator, much like our moon does to Earth. This is where the vampire analogy becomes horrifyingly real. The pulsar's immense gravitational pull acts like a siphon, relentlessly drawing material away from its companion star. This stolen gas spirals down onto the pulsar's surface, but the process doesn't end there. The act of accretion, of feeding on this matter, actually transfers energy to the pulsar, causing it to spin even faster. It's a feedback loop of destruction. The more it feeds, the stronger and faster it becomes, which in turn makes its feeding process even more efficient. However, the pulsar's radiation is so intensely powerful that it doesn't just pull material in. It also bombards the day side of its companion with enough energy to literally cook it, heating it to temperatures of over 10,000 degrees Fahrenheit and slowly boiling it away into space. This creates a spectacular and tragic visual, a small star with one half blisteringly bright and evaporating, and the other half cooler and dark. The discovery of this system was a triumph of multi-wavelength astronomy. It was first detected as a powerful source of gamma rays by NASA, a Fermi Gamma Ray Space Telescope. Gamma rays are the highest energy form of light, and their presence signaled an environment of extreme violence. Radio astronomers then followed up, using massive dishes to detect the incredibly precise, rapid-fire pulses emanating from the spinning neutron star. Optical telescopes provided the final piece of the puzzle, capturing the visible light from the system and revealing the telltale signs of the irradiated and evaporating companion star. By combining these different views, scientists were able to reconstruct the entire gruesome scene. The eventual fate of this system is as certain as it is bleak. The companion star, being slowly stripped of its mass, will eventually be whittled down to nothing. It may be completely vaporized by the pulsar's radiation or reduced to a mere planetary mass cinder, a dead husk of its former self. Once its meal is gone, the Black Widow pulsar will cease its spinning up process and will likely fly off into the galaxy as a hyper-rapid, lone millisecond pulsar, a silent monument to the solar system it destroyed. This cannibalistic process solves a long-standing mystery in astrophysics: how some pulsars achieve such incredibly fast rotation speeds. They aren't born spinning that fast, they are spun up by feasting on a companion. Visualizing this system is key to understanding its terrifying beauty. An animation would show the two stars in their tight orbit. We'd see a stream of gas like a celestial umbilical cord flowing from the companion star toward the pulsar. Then we'd see the pulsar's powerful particle winds a visible shock wave smashing into the companion's surface, creating a brilliant, heated face and blowing a comet-like tail of evaporated material out into the darkness behind it. This cosmic dance of death is a stark reminder that even among the stars, survival is a relentless and often brutal competition. From the intimate horror of a stellar vampire, we now expand our view to a predator of an entirely different scale, one that doesn't consume stars but entire galaxies. In the vast, relatively quiet suburban expanse of the Fornax cluster, about 60 million light-years from Earth, lurks a cosmic heavyweight with a dark and violent past. This is NGC 1316, a colossal elliptical galaxy that astronomers have identified as a confirmed cannibal, a galactic Goliath that has grown to its immense size by devouring its smaller neighboring dwarfs. The first clues to its monstrous nature are visible even in early telescopic images. Most giant elliptical galaxies are featureless, smooth balls of old red stars looking like immense fuzzy clouds. But NGC 1316 is different. When you look closely, you see intricate, complex structures etched into its heart. Most striking are the unusual, dark dust lanes that weave through its central region. This is the galactic equivalent of finding bones at a crime scene. In a pristine elliptical galaxy which forms from a hot, chaotic mess of gas, such cool, organized dust lanes should not exist. They are a clear sign of a recent and violent merger. These dust lanes are the shredded remains of a spiral galaxy that ventured too close, its cold, structured gas and dust torn apart and swallowed by the giant's overwhelming gravity, not yet fully digested and assimilated into the smooth population of the larger galaxy. But the evidence doesn't stop there. Even more telling are the faint, ghostly rivers of stars that surround NGC 1316. These are tidal streams, ethereal arcs of stars that have been gravitationally ripped from their parent galaxies during close encounters. They are the final, fading trails of the victims, stretched out across space over millions of years. spotting these requires the keen eye and deep exposures of telescopes like the Victor M. Blanco telescope in Chile, which can map the faintest light in the universe. These streams are the ultimate evidence of galactic cannibalism, the celestial version of finding a dust cloud on a dirt road after a struggle. They map out the history of the violence, showing the paths of the smaller galaxies as they were torn apart and absorbed. Perhaps the most fascinating forensic evidence comes from studying the galaxy's population of globular clusters. These are dense, spherical swarms of hundreds of thousands of ancient stars that orbit a galaxy's core like a swarm of bees. Normally, a large galaxy like this would be surrounded by thousands of these old, rich clusters. But NGC 1316 tells a different story. Its globular clusters are unusually faint and plentiful, and they exist in a much wider range of colors and ages than expected. This is the signature of a messy eater. When a large galaxy consumes a smaller one, it doesn't just acquire its stars, it also captures the victim's entire entourage of globular clusters. The cannibal galaxy ends up with multiple, distinct families of clusters from its various meals, creating a mixed and disordered population that betrays its violent history. It's like a serial killer's trophy case, with each unique cluster serving as a memento from a different conquest. This process of galactic cannibalism is not a rare or freak occurrence. It is the primary way galaxies grow and evolve. Our own Milky Way is currently in the process of digesting several smaller dwarf galaxies, like the Sagittarius dwarf spheroidal, which is currently being stretched into a long stellar stream that wraps around our galaxy. But the future holds a much larger feast. In about 4.5 billion years, the Milky Way is set to collide with our nearest large galactic neighbor, the Andromeda Galaxy. This will not be a fast, violent crash, but a slow, majestic dance over billions of years. The two spiral galaxies will first swing past each other, their gravitational forces pulling out long tails of stars and gas, much like the streams we see around NGC 1316. They will then swing back, merging again and again until they finally coalesce into a single, giant elliptical galaxy, a new cosmic titan that astronomers have nicknamed Milkomda. Our night sky from that far future Earth will be utterly transformed, the familiar band of the Milky Way replaced by a glowing, featureless ellipsoid of stars, a silent monument to a colossal act of cosmic consumption. To visualize the grandeur and violence of NGC 1316, deep field imagery is essential. We can see a side-by-side comparison, first showing a normal, smooth elliptical galaxy, then cutting to the complex, mottled, and dust-laden visage of the cannibal. Then, through advanced image processing, we can see the faint tidal streams illuminated, overlaying them as ethereal blue arcs encircling the galactic core, telling the story of its past meals. This galaxy is a stunning natural laboratory, a cosmic fossil that reveals the brutal, hierarchical nature of our universe, where the large consume the small to grow ever larger, in a cycle of creation and destruction that has been ongoing since the first stars began to shine. From the grand, galactic acts of cosmic cannibalism, we now travel back to the delicate, intricate rings of Saturn to witness a story of creation happening in real time. While Saturn is famous for its stunning rings and its many moons, it turns out these two iconic features are deeply connected. And right now, nestled within the bright bands of the ring, astronomers believe we may be witnessing the incredibly rare birth of a new moon, a tiny world they've affectionately nicknamed Peggy. The first hint of this extraordinary event came from NASA Cassini spacecraft, which spent over 13 years performing an unparalleled study of the Saturnian system. As it meticulously mapped the rings, its cameras spotted something peculiar. In the outermost region of the ring, there was a distinct, glaring irregularity. The normally impossibly smooth and orderly ring particles were showing a pronounced, chaotic disturbance. It wasn't a gap, but rather a bright, knotted feature, like a solitary bump or a scuff in a perfectly smooth sheet of ice. This anomaly was accompanied by a peculiar, propeller-shaped distortion in the ring material on either side of it. These propeller features were already known to scientists. They are the gravitational signatures of tiny, unseen moonlets, perhaps half a mile across, embedded within the rings. But this one was different. It was far larger and more disruptive than any propeller ever seen before. The leading theory, proposed by astronomer Carl Murray and his team after analyzing these Cassini images, is that we are seeing the gravitational wake of a nascent moon in its very earliest stages of formation. They believe this object, which they named Peggy in honor of Murray's mother-in-law, is a tiny, nascent moonlet, probably no more than a half-mile to a mile in diameter. It's not yet a fully formed, solid body, but rather a dense, growing snowball of ring material held together by its own weak gravity. Its presence creates a gravitational ripple effect, shepherding the fine ice particles around it and carving out that unique, propeller-shaped void in the rings as it travels along its orbit. It's the celestial equivalent of seeing a tiny pebble rolling through a field of fresh powder snow, pushing a small mound ahead of it as it moves. What makes Peggy so profoundly significant is that it offers us a front-row seat to a process we have only ever theorized about or seen the long finished results of. The leading model for the formation of Saturn's inner moons suggests they were born from the rings themselves. Billions of years ago, the rings were likely far more massive and extended. Within this vast disk of debris, particles would have collided and gently stuck together, a process known as accretion. Denser clumps would have grown, their gravity strengthening, allowing them to gather more and more material, eventually snowballing into full-fledged moons. Peggy appears to be a tiny, modern-day example of this exact process in action. We are witnessing moon formation in its infancy, a process that likely shaped much of the Saturnian system and offers a blueprint for how planets themselves coalesced from the disk of gas and dust around our young sun. Tragically, and adding a layer of poignant mystery to the story, we may never get a clearer look at Peggy. The Cassini mission concluded in 2017 with the spacecraft's intentional plunge into Saturn's atmosphere. Its final orbits took it closer to the rings than ever before, but it did not get another targeted opportunity to observe this specific anomaly. Furthermore, Peggy's fate is uncertain. The environment within the rings is a delicate balance of forces. It's possible that the very process that is creating it, its interaction with the ring particles, could also lead to its demise. The gravitational tides from Saturn itself might be pulling it apart, preventing it from ever growing into a larger, stable moon. It might even drift slowly outward over time, destined to leave its birthplace behind and join the family of small, shepherd moons that help define the edges of Saturn's rings. Visualizing this requires a blend of real data and informed artistic interpretation. We can see the actual Cassini imagery of the ring, with a bright arrow or circle highlighting the exact location of the disturbance, a tiny blemish on an otherwise flawless canvas. Then, an animated artist's concept can bring the theory to life, showing a close-up of a dense, rocky, icy core gently accumulating a mantle of bright, snowy ring particles, with clear gravitational wakes flowing away from it like the bow wave of a ship. This chance observation transforms Saturn's rings from a beautiful, static painting into a dynamic, evolving nursery, a place where worlds are still being born, reminding us that even in a solar system we think we know, the universe is still actively creating right before our eyes. Yet while the red rectangle presents a stunning example of cosmic geometry, it is far from the only one. In the constellation Serpens, another celestial wonder takes this mathematical perfection to an even more astonishing extreme. This is the Red Square Nebula, officially known as MWC 922, and it is perhaps the most perfectly symmetrical object ever discovered in deep space. Its name is a literal description, High-resolution infrared images reveal a structure so precisely square, with such sharp, ruler-straight rungs, that it looks less like a natural formation and more like a brilliant, glowing frame deliberately hung in the void. The nebula's symmetry is nothing short of breathtaking. At its heart lies a hot, dying star, a massive sun in its final act known as a pre-planetary nebula phase. As this star sheds its outer layers, the expelled material forms two opposing cones of gas and dust. Our viewing angle is the key to the magic. We are looking directly down the barrel of these cones, seeing them almost perfectly edge on. This perspective transforms the three-dimensional hourglass shape into a two-dimensional square, with the star itself sitting at the very center, the pinpoint of symmetry. The most stunning detail, captured in exquisite detail by the Hale telescope at Palomar Observatory, are the series of faint, equally spaced linear features that extend from the center, forming the rungs of the square. These are thought to be periodic outbursts from the central star, creating expanding shells that, when viewed from our special angle, appear as these perfect lines. But a square requires more than just an edge on hourglass. It demands an extraordinary level of fine-tuning. The leading theory to explain such crisp, clean geometry, again, involves a binary star system, though one that remains unseen. Astronomers suspect the central star has a companion whose gravitational influence acts like a master sculptor's tool, meticulously confining the outflowing material into such a narrow, precise bipolar structure. The companion star's orbit helps to focus the stellar wind into two extremely well-collimated jets, preventing the chaotic, spherical expansion that characterizes most dying stars. This process creates the sharp, defined edges of the square. The perfectly spaced rungs, meanwhile, are a cosmic echo of the central engine's rhythm. They are likely created by periodic pulsations or episodic mass loss from the dying star, with each pulse creating a new shell that expands outward. When these spherical shells are viewed edge-on through the narrow bipolar lobes, they appear as straight, bright lines, much like the rings of a tree trunk appear as lines when viewed from the side. The existence of objects like the Red Square Nebula and the Red Rectangle forces astronomers to reconsider the often messy and violent process of stellar death. We typically imagine supernova explosions or chaotic planetary nebulae, but these geometric wonders reveal that under very specific conditions, a binary interaction and a precise viewing angle, the death of a star can be a process of immense order and symmetry. They demonstrate that the laws of physics, when applied in a balanced system, can produce outcomes of breathtaking mathematical beauty. The surprise isn't that such structures exist, but that the chaotic universe can so frequently create conditions that allow for this level of perfection. Comparing these two red giants highlights a fascinating spectrum of cosmic geometry. The red rectangle shows us an X-shape with rungs, a structure born from a tight binary dance with a dense accretion disk. The red square presents a more filled-in, near-solid square with sharper corners, suggesting an even more tightly focused and powerful outflow. Other geometric nebulae, like the stunning Southern Crab Nebula with its hourglass figure, or the intricate and delicate structure of the engraved Hourglass Nebula, show that this phenomenon, while rare, is a repeatable outcome of stellar evolution. Each one is a natural laboratory, offering a slightly different recipe of stellar mass, binary separation, and orbital dynamics that results in its unique architectural form. To truly appreciate the sublime precision of the red square, detailed imagery is essential. Side-by-side comparisons with the red rectangle and other bipolar nebulae reveal the subtle but profound differences in their symmetry. An animation can bring the theory to life, starting with the central binary system, showing the focused bipolar jets erupting from the poles, and then illustrating how a series of perfectly timed outbursts create the expanding shells that, from our privileged vantage point, manifest as the nebula's iconic ladder-like rungs. It is a powerful reminder that the universe is not only a place of violent chaos, but also one of intricate order, where the final breath of a star can be exhaled as a near-flawless geometric form. And just as we witness the birth of new worlds within the rings of Saturn, our journey takes a turn into the profound darkness that lies between them, to confront one of the most compelling and unsettling ideas in modern cosmology, the concept of dark galaxies. Imagine an island in the cosmic ocean with the weight and gravity of a colossal metropolis like our Milky Way, but when you turn your telescope towards it, you see almost nothing. No glittering spiral arms, no brilliant hub of stars, just a ghostly, diffuse haze. This is not an empty void, it is a place dominated by an invisible king. This is the realm of a galaxy made almost entirely of dark matter. For decades, our understanding of galaxies was intrinsically tied to the stars they contained. We believed that where there was a galaxy's worth of gravity, there must be a corresponding galaxy's worth of starlight. That fundamental assumption was shattered with the discovery of objects like Dragonfly 44. Residing in the Coma cluster about 330 million light-years away, this enigmatic object was first spotted by a revolutionary telescope array, the Dragonfly Telephoto array, specifically designed to detect the faintest, most diffuse structures in the universe. To traditional telescopes, Dragonfly 44 was nearly invisible, but by studying the motion of the few stars it does possess, astronomers made a staggering calculation. The handful of stars in Dragonfly 44 are moving so rapidly that the gravity required to hold them together is immense. The conclusion was inescapable. This faint wisp of a galaxy has a mass comparable to our Milky Way, but 99.99% of that mass is invisible. It is a dark matter halo of epic proportions with just a tiny sprinkling of stars. So how do you find a galaxy that doesn't want to be seen? The methods are a testament to astronomical ingenuity. The primary tool is kinematics, precisely measuring the velocity of a galaxy's visible components. Stars and globular clusters orbit the galactic center, and their speed is a direct indicator of the total mass contained within their orbit. In a dark galaxy, you'll see a few stars or clusters moving at breathtaking speeds, implying they are whirling around in the grip of a deep, massive gravitational well that your telescope cannot see. Another method involves gravitational lensing. The immense mass of a dark galaxy, even without light, will warp the fabric of spacetime around it. When background light from more distant galaxies passes through this warped region, it is bent and distorted, creating telltale arcs and smears that betray the presence of the invisible mass. It's like seeing the silhouette of an object by watching how it distorts the view behind it. The existence of such objects poses a monumental challenge to our models of galaxy formation. The prevailing theory, the lambda cold dark matter model, beautifully explains the large-scale structure of the universe, but it predicts a haunting problem. It suggests there should be hundreds, even thousands, more small, dwarf galaxies orbiting large galaxies like the Milky Way than we actually see. This is known as the missing satellites problem. Dark galaxies like Dragonfly 44 could be the solution. They are the missing satellites. We just couldn't see them because they failed to form stars. This raises the even deeper question, why would a massive clump of dark matter, with all the gravitational potential to attract gas and form stars, fail to do so? The answer might lie in its environment. A dark galaxy born in a dense cluster might have had its primordial gas violently stripped away by the gravitational tides of larger galaxies or the searing heat of the intracluster medium before it could ever collapse into stars. It's a galactic stillbirth, a potential that was never realized, leaving behind a cosmic ghost, a skeleton of pure dark matter. This suggests that dark galaxies are not rare freaks of nature, but could in fact be incredibly common, perhaps even outnumbering the luminous galaxies we are familiar with. They would form the true, hidden backbone of the cosmic web, the dark scaffolding upon which the visible universe is built. Their discovery forces us to rewrite the story of galaxy evolution, acknowledging that for every brilliant spiral or elliptical we see, there may be numerous dark counterparts lurking just at the edge of perception, their immense mass silently shaping the cosmos from the shadows. To visualize this, picture an animated map of the Coma cluster, first showing only the bright, familiar galaxies. Then, a new filter is applied, revealing the gravitational field, and suddenly, the space between the glowing galaxies fills with faint, massive halos. Dark galaxies revealed only by their overwhelming gravitational presence, the true rulers of the cosmic deep. But just as we begin to map the hidden dark matter skeletons of our cosmos, our attention was suddenly pulled much closer to home by an object that was not hidden at all, but was merely passing through. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at unprecedented speed. Its trajectory was immediately calculated and found to be extraordinary. This was not an object from our solar system. It was the first interstellar visitor ever recorded, a traveler from the vast space between the stars, and it was given a name that reflected its role as a scout from afar, Oumuamua, Hawaiian for first distant messenger. From the very beginning, Oumuamua was an enigma. Its path was hyperbolic, meaning it was not bound by the sun's gravity and was only paying a one-time visit to our neighborhood. As telescopes around the world swiveled to observe it, the first major surprise was its shape. By measuring how its brightness changed dramatically as it tumbled through space, astronomers deduced it was highly elongated, perhaps 10 times as long as it was wide. This made it unlike any asteroid or comet we've seen in our own solar system, which tend to be more lumpy and rounded. It was a cosmic cigar, or perhaps a pancake, tumbling chaotically end over end. The biggest mystery, however, came as it departed. As Oumuamua sped away from the sun, something was wrong with its trajectory. After accounting for the gravitational pull of every planet and the sun itself, there was a small but significant extra push accelerating it away, a non-gravitational acceleration. In comets, this is a common effect caused by outgassing. As the sun heats a comet's icy surface, jets of gas erupt like tiny engines, nudging it off a purely gravitational path. The problem with Oumuamua was that we never saw this outgassing. There was no detectable coma, the fuzzy envelope of gas and dust that surrounds an active comet, and no evidence of the dust tail that would be expected from such activity. It was accelerating in total silence, as if by an invisible force. This is where the scientific debate ignited, creating a fascinating rift between conventional astrophysics and more speculative possibilities. The leading natural explanation is that Oumuamua was a comet after all, but one made of exotic ices. One compelling theory suggests it was composed largely of molecular hydrogen ice. Hydrogen ice is incredibly difficult to detect from afar. It would sublimate directly from solid to gas without releasing any visible dust or heavier molecules that our instruments could easily spot. This invisible outgassing could perfectly explain the non-gravitational acceleration without leaving a visible trace. Other theories propose it was a chunk of solid nitrogen, similar to the material found on Pluto, which would also sublimate in a hard-to-detect way, or even that it was a porous, fractal-like dust aggregate, a so-called dust bunny from deep space. Yet, for a small number of scientists, notably Harvard astronomer Avi Loeb, the natural explanations felt insufficient. He argued that the most extreme possibility, an artificial origin, should be considered. Could Oumuamua be a piece of alien technology? The most discussed concept was that of a light sail, a thin, reflective sheet designed to be pushed by the radiation pressure from stars. Its unusual shape and the fact that it seemed to be pushed by sunlight without any visible exhaust could, in theory, fit the profile of a derelict solar sail drifting between star systems. While this remains a highly controversial minority view, it underscores a profound point. Oumuamua was so strange that it forced us to confront ideas we might otherwise have dismissed. Regardless of its true nature, Oumuamua's visit was a paradigm-shifting event. It proved that interstellar objects are not rare. They are constantly passing through our solar system, and we simply haven't had the telescopes to find them until now. Its discovery has directly fueled plans for new missions, like the European Comet Interceptor, which is designed to wait in space for such an object to appear, ready to launch and rendezvous with it. It also changed planetary defense strategies overnight. We now know we must not only watch for asteroids from within our solar system, but also scan for potential incoming threats from the great beyond. To visualize this encounter, imagine an animation of our solar system with the familiar circular orbits of the planets. Then, from above the plane, see Oumuamua's path slash through at a steep angle, a straight line in a system of circles, whipping around the sun before being flung back out into the galaxy. We could see an artist's concept of its bizarre tumbling rotation, and a visual representation of the mysterious non-gravitational acceleration, perhaps shown as an invisible force vector pushing it just a little bit faster than gravity alone would allow. This silent, enigmatic visitor opened a new chapter in astronomy, reminding us that the galaxy is dynamic and full of moving pieces, and that sometimes the most profound discoveries arrive unannounced and leave us with more questions than answers. But if the silent, enigmatic journey of Oumuamua left us questioning what might be passing through our celestial neighborhood, our next discovery forces us to question the very foundation of our universe's birth. Imagine looking at a baby picture of the cosmos, a snapshot from its earliest infancy, and finding a blemish, a cold patch that simply shouldn't be there. This is the mystery of the cold spot, a vast and perplexing anomaly embedded in the oldest light we can see, the cosmic microwave background. This relic radiation is the afterglow of the Big Bang itself, a faint microwave hum that fills every corner of the universe, a cooled-down remnant from a time when everything was searingly hot and dense. Thanks to satellites like NAS, a Wilkinson microwave anisotropy probe, and the European Space Agency's Planck, we have incredibly detailed maps of this radiation. For the most part, it's remarkably uniform, with only tiny, random variations in temperature, the seeds that would one day grow into the galaxies and clusters we see today. But one region in the constellation Eridanus stands out starkly. It's a massive circular patch about 1.8 billion light-years across that is significantly colder than its surroundings. We're not talking about a fraction of a degree. This area is about 70 microkelvins cooler than the average, a substantial and deeply puzzling deviation. The immediate, most straightforward explanation was that this cold spot might not be a feature of the primordial universe at all, but rather an effect caused by something in the foreground. The leading candidate was a supervoid, an enormous region of space that is far emptier than it should be, containing far fewer galaxies and clusters. The theory goes like this: as light from the cosmic microwave background travels through the universe on its way to us, it must climb in and out of the gravitational wells created by large clumps of matter. Climbing out of a well costs the photon energy, causing it to redshift, which we perceive as a slight cooling. If this light passed through a truly vast void, a region of below-average density, it would actually gain energy falling into the under-dense area, but then lose less energy climbing out than it would have in normal space. This integrated Sachs-Wolf effect would result in a net gain of energy, making the light appear slightly warmer, not colder. To explain a cold spot, you'd need the opposite. Some physicists proposed a more nuanced version. If a supervoid were expanding faster than the surrounding universe due to its lack of gravitational pull, it could create an additional cooling effect. The hunt was on to find this hypothesized supervoid, and indeed, large-scale galaxy surveys did find a significant underdense region in the general direction of the cold spot. But here's the catch: it's not nearly big enough or empty enough to account for the dramatic temperature drop we observe. The void we've found might contribute to the cooling, but the math simply doesn't add up. It can only explain a fraction of the effect. This discrepancy is the heart of the mystery. The cold spot's intensity challenges the standard cosmological model, which has a hard time explaining how such a large and anomalously cold region could have formed through random chance in the early universe. This is where the theories become truly spectacular. If a foreground supervoid can't fully explain it, perhaps the cause is imprinted on the CMB itself, a relic from the universe's first moments. One extraordinary possibility is that the cold spot is a bruise, a cosmic scar from a collision with another universe. This idea springs from the multiverse hypothesis, a consequence of certain theories of eternal inflation. In this mind-bending scenario, our universe is just one bubble in a vast, frothing meta-universe where new bubbles are constantly inflating into existence. If another bubble universe collided with ours in the distant past during the inflationary epoch, the energy released in that collision could have left a distinct imprint on our cosmos, a specific, circular pattern of temperature variation. The cold spot fits the profile of such an imprint. It would be the first empirical evidence that our universe is not alone, that there is a greater, unobservable cosmos beyond our own. Other, less exotic but still fascinating theories have been proposed. It could be the signature of a cosmic texture, a knot in the very fabric of space-time that formed during a phase transition in the early universe, a flaw in the cosmic structure that would have a unique gravitational signature. Or it could simply be a rare statistical fluke, a 1 in 1,000 chance that just happened to occur in our observable universe. But with each passing year and more precise data, the fluke explanation becomes less and less satisfying to many scientists. The ongoing research to solve this puzzle is a beautiful example of multi-pronged scientific investigation. Cosmologists are creating ever more sophisticated computer simulations of the universe to see if the standard model can, against all odds, produce such a feature naturally. Astronomers are using the world's most powerful telescopes to conduct deeper and more complete surveys of the galaxies in the cold spot's direction, searching for any previously unseen structure that could account for the anomaly. And theoretical physicists are refining their models of inflation and the multiverse, working out the precise observational signatures a bubble collision would leave behind. Visualizing this is essential to grasp its profound implications. An animation would start with the full sky Planck map of the cosmic microwave background, a mottled oval of reds and blues representing the tiny temperature fluctuations. The camera would then zoom in on the cold spot, a large circular blue region that clearly stands out. We could then see a model of the hypothesized supervoid in the foreground, represented as a transparent, spherical bubble, and watch as light rays from the CMB pass through it, demonstrating why its effect is too weak. Finally, we could see an artist's concept of the multiverse collision, our universe as one bubble, with another bubble approaching and making contact, a shockwave of energy rippling through the infant cosmos and freezing into the pattern we see today. Whether a flaw in the data, a rare void, or a window into the multiverse, the cold spot remains one of cosmology's most tantalizing puzzles, a chilling reminder that our universe's first light may still hold secrets capable of rewriting everything we think we know. After confronting the possibility that our universe's oldest light might bear the scars of a collision with another cosmos, we now turn to a stellar event that defies the most fundamental rules of cosmic death. In our universe, when a star goes supernova, that's supposed to be the final, dramatic end. It's a singular, catastrophic explosion that tears the star apart, blasting its remains into space and leaving behind, at best, a dense neutron star or a black hole. The star does not get a second act, but in September 2014, the Intermediate Palomar Transient Factory Survey spotted something in a galaxy 500 million light-years away that shattered this foundational belief. They designated it IPTF-14 HLS, a name that belies the sheer pandemonium this object would unleash. It looked at first like a completely ordinary Type II supernova, the kind caused by the core collapse of a massive star. It brightened, it peaked, and then, instead of steadily fading into obscurity over 100 days as every known supernova had done before it, it did the unthinkable. It brightened again, and then again and again. For over 600 days, this stellar corpse repeatedly rose from the grave, earning it the unforgettable nickname, the Zombie Star. The light curve of IPTF-14 HLS is a thing of bizarre beauty, a wild roller coaster that completely broke the mold. Astronomers watched in utter disbelief as it went through at least 5 distinct peaks in brightness over 2 years, with its luminosity soaring and plunging as if the star was having multiple explosive fits. To put this in perspective, a normal supernova explosion releases a staggering amount of energy all at once on the order of 10 to the 44 joules. The total energy radiated by IPTF-14 HLS over its long, fitful duration was calculated to be 10 times that amount. It was outputting more energy than should have been physically possible from a single core collapse event, as if the star had a hidden engine that kept refueling the explosion. This wasn't a death, it was a sustained, chaotic tantrum of a star that refused to die quietly. Explaining this required physicists to venture into the realm of extreme and rarely tested stellar theories. The leading hypothesis involves a phenomenon called pulsational pair instability. This occurs in the hearts of the most massive stars in the universe, those born with between 95 and 130 times the mass of our Sun. In such behemoths, the core becomes so hot that light itself begins to spontaneously transform into matter, creating pairs of electrons and their antimatter counterparts, positrons. This process removes the radiation pressure that was holding the star up against its own immense gravity. The core becomes unstable and begins to collapse, triggering a massive thermonuclear explosion. But in this model, the explosion isn't strong enough to completely unbind the entire star. It instead blows off the star's outer layers in a colossal eruption, after which the core cools, stabilizes, and continues on for years or even decades. Then the process repeats. The star experiences multiple violent pulses, each one ejecting a shell of material. When the next pulse occurs, it slams into the previous shell, creating a new bright flash. This could continue until the star's mass is reduced enough to finally undergo a true, final core collapse supernova. IPTF-14 HLS could have been the first observed example of this theoretical death spiral. Other theories are just as compelling. Perhaps the supernova created an extremely powerful magnet, a neutron star spinning hundreds of times per second with a magnetic field a quadrillion times stronger than Earth. The incredible rotational energy of such an object, fed into the expanding supernova ejector, could provide the long-term engine needed to re-brighten the explosion multiple times. Or perhaps the star had an unusually extended and dense structure, like a series of onion shells, and the supernova shockwave took an exceptionally long time to heat and break out through each layer, creating the observed series of peaks. The true challenge of the zombie star isn't just explaining its energy output, it's what it means for our entire classification system of stellar explosions. Supernova taxonomy is built on the assumption that certain observational features, light curve shape, chemical signatures point to a specific physical cause. IPTF-14 HLS looked like a standard Type II supernova in its spectrum, but its light curve was from another dimension altogether. It forces astronomers to admit that the same spectral signature can hide a multitude of wildly different physical processes. It tells us that our categories are merely sketches, and that nature, in its infinite creativity, can produce outliers that render our neat classifications utterly inadequate. This one object single-handedly demanded that we reconsider what we thought was a settled chapter of stellar evolution. proving that even in death, the biggest stars can still hold shocking secrets. But if a zombie star represents a chaotic and prolonged rebellion against death, then our next discovery is the ultimate authoritarian, a cosmic dictator that rules not with fire, but with an invisible, crushing force of will. Imagine a star so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. Now, take that already unimaginable object and arm it with the most powerful magnetic field in the known universe, a field so intense it can literally tear atoms apart from 1,000 kilometers away and warp the very fabric of empty space. This is not science fiction. This is a magnetar, a neutron star that has crossed over into a realm of such extreme physics it has earned the nickname magnetic monster. The numbers involved are so large they border on the absurd. A typical magnetar possesses a magnetic field measuring in at around 1 quadrillion Gauss. To grasp that, consider that a strong refrigerator magnet is about 100 Gauss. The Earth's protective magnetic field is a gentle 1 Gauss, the most powerful magnetic field we can sustainably create in a laboratory using massive, room-sized electromagnets, reaches about 1.2 million Gauss. A magnetar's field is 1 trillion times stronger than that. This isn't just a strong magnet, it's a fundamental force of nature. At this level, the magnetic field ceases to be a simple invisible force and starts to have tangible, terrifying effects on the structure of reality itself. The field is so powerful it can distort the electron clouds of atoms, stretching them into long, thin, needle-like cylinders, effectively making chemistry impossible in its vicinity. It can even catalyze a process called photon splitting, where a single particle of light passing through the magnetic vacuum is split into 2 or more photons, an effect predicted by quantum electrodynamics but only possible in the presence of such godlike fields. This unimaginable power is not just a dormant threat. It expresses itself in sudden, catastrophic tantrums known as starquakes. A magnetar is the crystallized, ultra-dense remnant of a supernova, and its solid crust, under immense strain from the slowing of its rotation and the immense magnetic forces within, can fracture. Think of it like a tectonic plate on Earth, but under pressures 1 billion times greater. When this star-sized crust snaps, it unleashes a cataclysm. The resulting explosion, a magnetar flare or giant flare, is beyond comprehension. In a mere fraction of a second, one of these events can release more energy than our Sun will emit across 100,000 years. It is the single most violent and luminous transient event known to occur in the present-day universe, second only to the Big Bang itself in its raw, instantaneous power. And we are not immune to their distant fury. On December 27, 2004, a magnetar named SGR 180620, located 50,000 light-years away in the constellation Sagittarius, had a starquake. The radiation from this event, a flash of gamma rays and X-rays, washed over our solar system. It was so powerful that it actually compressed Earth's magnetic field on the day side of the planet and ionized the upper atmosphere, disrupting long-range radio communications. If this flare had occurred from a source just 10 light-years away instead of 50,000, it would have likely stripped our planet of its ozone layer, triggering a mass extinction event. A magnetar in our stellar neighborhood is one of the few natural phenomena that could pose an existential threat to all life on Earth, a sobering reminder of the violent potential contained within these exotic objects. The very existence of such magnetic monsters forces us to answer a difficult question. How does nature build such an impossibly powerful magnet? The leading theory points to a perfect storm of conditions during the supernova death of a highly massive, rapidly spinning star. As the star's core collapses, its already existing magnetic field is squeezed and wound up, a process astronomers call the dynamo effect. If the progenitor star was spinning fast enough and had a strong initial magnetic field, this dynamo can be amplified to ludicrous levels during the chaotic few seconds of collapse, essentially freezing an impossibly intense magnetic field into the newly born neutron star. Another, more exotic theory suggests that a bizarre state of matter might exist in the core of a neutron star, a soup of free quarks rather than confined neutrons. If this quark matter exists, it could be a superfluid and superconductive, allowing electrical currents to flow without resistance and generating a perfectly stable, eternal magnetic field of unimaginable strength. This is why magnetars are more than just cosmic curiosities. They are unparalleled natural laboratories. They allow us to study the behavior of matter, energy, and forces under conditions so extreme we could never hope to replicate them on Earth. We can test the limits of quantum electrodynamics, observe the structure of a vacuum under strain, and probe the very equation of state of ultra-dense matter. Every flicker, every flare, and every pulse from these magnetic monsters sends us valuable data from the edge of physical possibility, teaching us about the fundamental laws that govern our universe written in the language of violence. Yet from a star that defies death and a magnetar whose fury could sterilize worlds, we plunge into an even more dramatic cosmic scene. A supermassive black hole, the very anchor of a galaxy, caught in the act of a desperate escape. This is the incredible story of a runaway black hole, a cosmic behemoth that appears to have been violently ejected from the heart of its own galaxy, fleeing into the void at unimaginable speed and leaving a brilliant, paradoxical trail of newborn stars in its wake. The discovery was made using the Hubble Space Telescope, and the initial observation was so bizarre that astronomers first thought it was an imaging artifact, a cosmic scratch on the lens. But the data was real. They were looking at a galaxy about 8 billion light-years away when they spotted a linear feature, a perfectly straight, bright streak shooting out from its core. At the tip of this streak was a brilliant, compact source of light, a quasar, the intensely luminous accretion disk of a supermassive black hole actively feeding on gas. The stunning revelation was that this quasar was not sitting peacefully at the galaxy's center. It was moving fast. Calculations showed it was traveling at nearly 5.6 million miles per hour, a speed so tremendous it could fly from Earth to the Moon in under 15 minutes. Even more astonishing was the streak itself. This wasn't a trail of destruction, it was a corridor of creation. Spectroscopy revealed it was composed of ionized oxygen, glowing brilliantly not from the heat of violence, but from the intense radiation of brand-new, massive blue stars. The runaway black hole was blazing a path through space, and somehow it was building a stellar highway behind it. The immediate, pressing question is one of pure physics. How do you kick a black hole that can weigh billions of times more than our Sun? The force required is almost beyond calculation. The leading theory involves the most powerful energy release mechanism in the universe since the Big Bang, the asymmetric emission of gravitational waves. This recoil effect is predicted by Einstein's general relativity and occurs during the merger of two black holes. As they spiral inward and finally collide, they emit gravitational waves, ripples in the fabric of spacetime. If the two black holes are of unequal mass or have misaligned spins, these waves can be shot out more powerfully in one direction than another. To conserve momentum, the newly merged, larger black hole recoils in the opposite direction, like a rocket firing its engine. In an incredibly energetic merger, this gravitational wave kick could be powerful enough to overcome the immense gravitational pull of the galaxy's core and literally launch the black hole into intergalactic space. It's a cosmic cannon firing the universe's most terrifying projectile. This incredible event reveals the hidden, violent dynamics at the heart of galaxies. Most large galaxies are thought to harbor a central supermassive black hole, and when galaxies collide, their black holes eventually sink to the center of the new merged galaxy through a process called dynamical friction. They then form a binary pair destined to eventually merge. The discovery of a runaway black hole is the first strong observational evidence that this process doesn't always end quietly. Sometimes it ends with a cataclysmic kick that can disrupt the entire galactic nucleus, leaving behind a galaxy with no central black hole at all, a ghost ship without its anchor, destined to evolve in unpredictable ways. But the most beautiful and counterintuitive part of this story is the trail of stars. How does a voracious gravitational predator become a catalyst for creation? The leading explanation is that the speeding black hole is plowing through a vast reservoir of dense, cold gas that surrounds its host galaxy. As it rams through this gas at hypersonic speed, its immense gravity compresses the gas clouds in its path, shock heating some of it to feed its own accretion disk and causing the quasar to flare brightly. But along the edges of this cosmic wake, the compression is just right to trigger the collapse of gas clouds, igniting a firestorm of star formation. It's analogous to the process that creates jellyfish galaxies, but on a much more focused and dramatic scale. The black hole is not consciously creating stars. It is a force of nature whose passage happens to create the perfect conditions for new suns to ignite in its turbulent aftermath. The potential future for such an object is a lonely one. If its velocity exceeds the galaxy's escape velocity, which this one certainly does, it will never return. It will become an intergalactic wanderer, a rogue supermassive black hole drifting through the profound darkness between the galaxies. It may eventually carry its luminous quasar glow for millions of years until it exhausts its supply of entrained gas, at which point it will fade to black, becoming an invisible titan adrift in the void. Perhaps it will eventually be captured by another galaxy in the distant future, starting the cycle anew. To visualize this epic journey, imagine an animation showing the chaotic merger of two galaxies, their black holes spiraling together and merging with a flash of gravitational waves. Then see the new, larger black hole recoil, shot out of the galactic core like a bullet. As it speeds through the galaxy's outer gas halo, we see a brilliant wake of blue light erupting behind it. Not fire, but the birth of countless new stars, a stunning legacy of its violent departure. But while our own solar system hosts visitors of profound mystery, it also holds worlds of astonishing complexity right in our cosmic backyard. We now turn from interstellar wanderers to the king of the planets itself, Jupiter, a gas giant that continues to reveal atmospheric secrets far stranger than we ever imagined. Beyond its banded clouds and the raging fury of the Great Red Spot, astronomers have discovered a massive, invisible feature in the planet's upper atmosphere, a colossal, fluctuating cold region aptly named the Great Cold Spot. This feature wasn't found by looking at visible light. It was uncovered through the precise, temperature-sensing eyes of infrared telescopes, specifically the Cryo's instrument on the Very Large Telescope in Chile. By meticulously mapping the heat signature of Jupiter's thin upper atmosphere, known as the thermosphere, scientists noticed a persistent dark blotch, a region significantly cooler than its surroundings. The scale of this spot is staggering. It spans up to 24,000 kilometers across at its greatest extent, making it large enough to comfortably swallow the entire Earth whole. This isn't a storm in the familiar sense with swirling clouds and convection. It's a vast, subtle anomaly in the planet's heat distribution, a profound atmospheric puzzle hiding in plain sight. What makes the Great Cold Spot so baffling is its behavior. It fluctuates dramatically in both size and shape, sometimes appearing as a near-perfect circle, and at other times stretching into a more complex, contorted form. Yet, despite these changes, it has remained anchored to the same general region of the planet's aurora for at least 15 years, and likely much longer, suggesting it's a permanent, though dynamic, feature of Jupiter's weather system. This independence is key. It doesn't correlate with the planet's famous lower atmosphere storms or its daily weather patterns. It exists in a realm of its own, governed by a completely different set of rules, a ghostly signature etched into the upper air. So what could possibly create and sustain such a massive cold anomaly? The leading theory points directly to Jupiter's powerful and spectacular auroras. Unlike Earth's auroras, which are powered by solar wind particles, Jupiter's are primarily driven by its own volcanic moon, Io. Io constantly spews material into space, which becomes ionized and trapped by Jupiter's immensely powerful magnetic field. These particles are then funneled down to the planet's poles, where they slam into the atmosphere and create a permanent, dazzling auroral glow. This process doesn't just create light, it also pumps tremendous energy into the atmosphere, heating the gases around the poles. Scientists believe this intense, localized heating might actually trigger a global circulation pattern. To balance out this energy input, the atmosphere may be responding by creating a vast region of cooling, a giant upper atmospheric vortex that acts as a radiator, shedding excess heat back into space. The Great Cold Spot could be the manifestation of this planetary cooling system, a counterintuitive side effect of the most powerful auroral activity in the solar system. Other theories are also being explored. Could it be the result of atmospheric waves generated by the turmoil deeper in Jupiter's atmosphere that propagate upward and break in the thermosphere, depositing their energy and altering the temperature? Or is it a unique form of vortex, a stable structure that can persist in the thin upper atmosphere, similar to the way the Great Red Spot persists lower down, but operating under a completely different set of physical principles? The truth is, we simply don't know yet, and that's what makes this discovery so thrilling. The existence of the Great Cold Spot fundamentally changes our understanding of gas giants. We can no longer view their weather systems as being confined to the colorful cloud decks we see. There is a whole other layer of atmospheric dynamics occurring high above the storms, a complex interplay between magnetic forces, auroral energy, and global heat distribution that we are only beginning to detect. It suggests that similar features might exist on other gas giants like Saturn, and it forces us to consider that the atmospheres of these planets are deeply interconnected, three-dimensional systems from their turbulent hearts to their ethereal outer edges. To visualize this, imagine an animation of Jupiter first showing the familiar face with its great red spot. Then we'd fade in an infrared overlay, revealing the brilliant hot rings of the auroras at the poles, and then, much further away from the pole, the distinct deep blue signature of the Great Cold Spot, a silent, massive shadow in the upper atmosphere, a testament to the hidden and complex forces forever shaping this colossal world. But if Jupiter's Great Cold Spot reveals a hidden layer of atmospheric complexity, our next mystery forces us to contemplate the entire cosmos and uncover a fundamental truth so shocking that it has completely rewritten the destiny of the universe. This is the ultimate puzzle of modern science, the discovery that not only is our universe expanding, but that this expansion is accelerating, pushed apart by an unknown, repulsive force that has been given a simple yet profoundly mysterious name: dark energy. The story of this discovery begins in the late 1990s with two independent teams of astronomers who were engaged in a seemingly straightforward task: measuring the rate of the universe's expansion over time. Their tool was a specific type of stellar explosion, a Type 1 supernova. These are the thermonuclear detonations of white dwarf stars, and they have a remarkable property: they all reach nearly the same peak brightness. This makes them perfect standard candles, just as you can tell how far away a car is by how dim its headlights appear. Astronomers can measure the distance to these supernovae by how dim they appear from Earth. By looking at supernovae in extremely distant galaxies, they were effectively looking back in time. The plan was to see how much the expansion of the universe had slowed down over billions of years due to the collective gravitational pull of all the matter within it. The expectation was unanimous: gravity would be putting the brakes on the cosmos. What they found instead sent a shockwave through the world of physics. The distant, ancient supernovae were fainter than their models predicted. This meant they were further away than they should have been. There was only one possible explanation: the expansion of the universe wasn't slowing down at all. In the latter half of its life, the universe had somehow stepped on the accelerator. The expansion was speeding up. It was as if you threw a ball into the air, and instead of slowing down and falling back to Earth, it shot away from you faster and faster into the sky. This discovery was so counterintuitive and so revolutionary that it earned the leaders of the two teams the Nobel Prize in Physics in 2011. We had been completely wrong about the ultimate fate of the cosmos. The force behind this acceleration was dubbed dark energy. We don't know what it is, but we can measure what it does. Its most defining characteristic is that it possesses a strong negative pressure. While matter and energy that we're familiar with create attractive gravity that pulls things together, this negative pressure generates a repulsive gravity that pushes space itself apart. Think of it as a kind of anti-gravity woven into the very fabric of the vacuum of space. The most staggering detail is its dominance. Current measurements indicate that dark energy makes up about 68% of the total mass energy content of the universe. Dark matter makes up about 27%. That means everything else, every star, every planet, every galaxy, every atom that makes up you and me, and everything we have ever observed with every telescope in history comprises less than 5% of the universe. We are living in a cosmos dominated by entities we cannot see and do not understand. So what is this mysterious force? The leading candidate is the cosmological constant, an idea first proposed by Einstein and later discarded as his greatest blunder. This concept suggests that empty space is not truly empty. It is seething with a constant intrinsic energy, a property of the vacuum itself. This energy would exert a negative pressure, causing space to expand. The problem is one of scale. When quantum physicists try to calculate the predicted value of this vacuum energy, their answer is off by a factor of 10 to the power of 120. That is a number so unimaginably large it is the greatest discrepancy between theory and observation in all of science. Other theories propose that dark energy is not a constant, but a dynamic field that changes over time, often referred to as quintessence. This would be a new kind of force field that permeates space, similar to the Higgs field, but one whose energy density can evolve, potentially weakening or strengthening as the universe ages. There are even more exotic ideas, such as the possibility that our theory of gravity itself, Einstein's general relativity, is incomplete on the largest cosmic scales and needs to be modified to account for what we see. Each possibility leads to a radically different future for our universe. A true cosmological constant means the acceleration will continue forever, leading to a cold, isolated, and empty heat death. An evolving quintessence field could potentially reverse, leading to a big crunch, or it could grow stronger and ultimately tear apart every atom in the universe in a big rip. Unraveling this mystery is the primary goal for a new generation of ambitious astronomical projects. The Vera C. Rubin Observatory will conduct a relentless, decade-long survey of the sky, mapping the positions and distances of billions of galaxies to trace the history of cosmic expansion with unprecedented precision. The Nancy Grace Roman Space Telescope will hunt for distant supernova, going even further back in time than the original discoveries. The Euclid spacecraft is already measuring the subtle distortion of galaxy shapes caused by dark matter, which is also influenced by the rate of expansion, building a three-dimensional map of the dark universe. These instruments won't take a direct picture of dark energy. Instead, they will measure its effect on the growth of the universe's large-scale structure over billions of years, hoping to find a tiny fingerprint in the data that points toward one theory and away from the others. The search for dark energy is a profound reminder that we are living in a golden age of cosmology, a time when our most basic questions about the nature of reality itself are still wide open, waiting for a moment of brilliance, a new observation, to finally point the way toward an answer. Yet for all the grand mysteries of dark energy shaping the entire cosmos, some of the most compelling puzzles remain tantalizingly close to home, hidden in the frozen, dark reaches of our own solar system. This brings us to a modern astronomical detective story, a hypothesis born not from a direct observation, but from the ghostly gravitational fingerprints of an unseen giant. This is the hunt for Planet 9, a theoretical world whose existence is inferred solely from the strange, clustered orbits of small, icy bodies far beyond Neptune. The evidence for this potential planet begins with a group of objects known as extreme trans-Neptunian objects, or ETNOS. These are small, icy worlds orbiting in the distant Kuiper belt and the even more remote Oort cloud. Their orbits are incredibly elongated, taking them thousands of years to complete a single journey around the Sun. For the longest time, the handful of these objects we had discovered seemed to have random, unrelated paths. But in 2016, Caltech astronomers Konstantin Batygin and Mike Brown noticed something peculiar. When they plotted the orbits of the 6 most distant known ETNOS, they didn't point in random directions. Instead, their points of closest approach to the Sun, their perihelia, all clustered together in the same general region of the sky. Even more strangely, their orbits were all tilted in a similar way, leaning over at roughly the same angle. The probability of this particular clustering happening by pure chance was calculated to be around 0.0007% astronomically small. It was as if someone had drawn a giant, invisible magnet in the outer solar system, shepherding these tiny orbits into a specific, coordinated alignment. The most elegant and dramatic explanation for this bizarre clustering is the gravitational influence of a massive, undiscovered planet. Batygin and Brown's models suggest this world would be a true giant, with a mass roughly 5 to 10 times that of Earth, placing it somewhere between a super-Earth and a mini-Neptune, a class of planet common around other stars but conspicuously absent in our own solar system. Its orbit would be equally colossal and eccentric, taking it on a 15,000-year loop around the Sun. At its closest approach, it might come within 200 astronomical units of the Sun, but at its most distant, it could be over 1,200 AU away, plunging into the inner Oort cloud. From our perspective, this world would move so slowly against the backdrop of stars that it would be incredibly difficult to spot, a faint ghost creeping through the darkness. The search for this hypothetical world has become one of astronomy's great modern quests, employing some of the most powerful telescopes on Earth, like Subaru in Hawaii and the Victor M. Blanco telescope in Chile. Astronomers are not looking for a bright, obvious point of light. They are engaged in a painstaking process of scanning vast swaths of the sky, taking images nights or weeks apart, and looking for one incredibly faint star-like object that has moved just a tiny, almost imperceptible amount. It is a needle in a haystack search on a cosmic scale, complicated by the fact that we don't know exactly where in its enormous orbit the planet might be. The search is further hampered by our own galaxy. The plane of the Milky Way is a dense, star-rich region that creates a formidable backdrop of light, making it even harder to pick out a single, slow-moving dot. Naturally, a claim this extraordinary has sparked intense debate and prompted scientists to explore alternative explanations. Could the orbital clustering be an observational bias? Perhaps our surveys have only looked in certain parts of the sky, and as we discover more of these distant objects, the apparent clustering will disappear, averaging out into a random distribution. Other theories are far more exotic. Some physicists have proposed that the gravitational anomalies could be explained not by a planet, but by a primordial black hole, a leftover relic from the Big Bang with a mass similar to a planet but compressed into an area smaller than a baseball. This dark, dense object would have the same gravitational effect but would be completely invisible to optical telescopes, only potentially detectable by the Hawking radiation it might emit or by the gamma ray flashes from annihilating dark matter if it passed through a dense cloud. Another, less dramatic possibility is that the collective gravity of many smaller, unseen Kuiper belt objects could, over billions of years, have sculpted the orbits of the ones we see into their current strange alignment. The implications of actually finding Planet 9 would be nothing short of revolutionary for our understanding of the solar system's history. Its existence would solve several long-standing puzzles. For instance, it could explain the unusual tilt of the solar system's plane relative to the Sun and the mysterious orbital angle of a few other detached objects like Sedna. But it would also create a profound new mystery. How did it get there? A planet of that size could not have formed so far from the Sun in the sparse protoplanetary disk. The most likely scenario is that it formed much closer in, alongside Jupiter and Saturn, and was then violently kicked out into its current distant orbit by a gravitational slingshot interaction with those gas giants in the early, chaotic days of the solar system. Its discovery would force us to completely rewrite the narrative of our solar system's violent youth, a time of planetary pinball that ejected a giant world into the eternal frozen night. Finding it would not just be about adding a new planet to textbooks, it would be like finding a lost chapter of our own cosmic origin story, a fossil from a time of upheaval that shaped the familiar system we call home today. While the violent drama of galactic cannibalism often plays out in distant clusters, the most compelling evidence for this cosmic predation is written in the stars right above our heads. Our very own Milky Way, that familiar, shimmering river of light in the night sky, is not the serene and stable island universe it appears to be. It is a celestial Goliath with a violent history, a galaxy built over billions of years through the relentless consumption of its smaller neighbors. And we now have the technology to read the forensic evidence of these ancient collisions, to see the ghostly remains of devoured galaxies still swirling around us, telling a story of our own violent origin. This revolutionary evidence comes in the form of stellar streams, vast, river-like structures of stars that orbit the galactic center, tracing out the paths of long-lost galaxies. These are not random clusters, they are the shredded remnants of dwarf galaxies that ventured too close to the Milky Way's immense gravitational pull. Over billions of years, our galaxy's tidal forces have stretched and torn these smaller systems apart, pulling their stars out into long, elegant arcs that now encircle our galactic home. For a long time, these streams were theoretical, their faint light lost in the overwhelming glare of the Milky Way's own stars. That all changed with a single spacecraft, the European Space Agency's Gaia mission. Gaia is arguably one of the most important astronomical instruments ever built. Its purpose is deceptively simple yet monumentally ambitious: to create a three-dimensional, dynamic map of over 1% of the stars in our galaxy. It doesn't just measure their positions, it precisely tracks their movements, their velocities, and their distances. This unprecedented census has given us a god's-eye view of the Milky Way's structure and its history. By analyzing Gaia's incredibly precise data, astronomers can now identify groups of stars that are moving together through space, stars that share a common velocity and trajectory that marks them as outsiders, as survivors from a shared cataclysmic past. Two of the most dramatic examples of these galactic fossils are the Sagittarius stream and what astronomers call the Gaia sausage or Gaia Enceladus. The Sagittarius dwarf spheroidal galaxy is a victim we can watch being consumed in real time. This small galaxy was discovered in the 1990s, and observations show it is currently in the process of being ripped apart. Its stars have been drawn out into two magnificent, opposing streams that completely encircle the Milky Way like a strand of cosmic pearls wrapped around a giant. This stream is so vast that it constitutes one of the largest structures in the entire night sky, a testament to the sheer scale of this ongoing destruction. But the Gaia sausage reveals an even more ancient and violent chapter. This discovery was a complete surprise that emerged from the early Gaia data. Astronomers found that a significant portion of the stars in our galaxy's inner halo, the diffuse cloud of stars that surrounds the central bulge, were not moving on random orbits. Instead, they were shooting back and forth on extremely radial, elongated paths, like commuters on a celestial highway running directly toward and away from the galactic center. When plotted in a graph of velocity versus angle, these stars clustered together in a shape that resembled a sausage. This was the unmistakable signature of a single colossal merger event. The theory suggests that between 8 and 11 billion years ago, a massive dwarf galaxy, perhaps as large as 1/3 the mass of the Milky Way's disk at the time, slammed directly into our young galaxy. This was not a glancing blow, it was a head-on collision of staggering proportions. The impact likely drastically reshaped the early Milky Way, puffing up its disk to help form the halo and funneling a huge amount of gas and stars toward the center. The concept that emerges from these discoveries is known as hierarchical accumulation. It is the dominant theory of how all large structures in our universe form. Galaxies are not born in isolation, fully formed as the beautiful spirals we see today. They grow like cosmic snowballs, starting as small clumps of dark matter and gas in the early universe. Gravity pulls these clumps together, they merge, they collide, and they accumulate more and more material. The larger galaxies consume the smaller ones, growing ever more massive in a cycle of creation through destruction. The stellar streams we see are the final, fading evidence of this process. They show us that the Milky Way's history is written in the stars of its victims, a layered archaeological record of its growth. And this process is far from over. The Milky Way is currently digesting these remains. The stars from the Sagittarius stream and the Gaia sausage are gradually being scattered, their unique orbital signatures being erased as they mix with the native population of the galactic halo. Their identities are slowly fading, but their chemical makeup gives them away. Stars formed in different galaxies often have distinct chemical fingerprints, ratios of elements that reflect the conditions of their birth cloud. So even as their motions become randomized, their elemental DNA continues to tell the story of their extragalactic origin. This means our own solar system is orbiting within a galaxy that is still dynamically active, still assimilating the remains of its ancient conquests. It's a profound realization that we live not in a static universe, but in one that is continuously evolving, with our own galaxy serving as both a museum of cosmic history and an active site of galactic integration. And now we pivot from the ancient, slow-motion drama of galactic cannibalism to a phenomenon of breathtaking speed and ferocity, a cosmic flash so powerful it can outshine an entire galaxy for a few thousandths of a second. These are fast radio bursts, or FRB, and among their already strange ranks, a select few are the strangest of all, the repeaters. These are not one-off explosions, they are persistent, unpredictable cosmic chatterboxes, sending out their immensely powerful signals again and again, defying our every attempt to explain them with known physics. The story of FRBs began in 2007, when astronomer Duncan Lorimer was sifting through archived data from the Parkes radio telescope in Australia, searching for new pulsars. He found something entirely unexpected, a single colossal burst of radio energy that lasted just 5 milliseconds. In that sliver of time, it released as much energy as the sun does in 80 years. For over a decade, every new FRB discovered was a singular event, a cosmic firecracker that flashed once and was never heard from again. The leading theories pointed to the most violent, destructive events imaginable: the collision of two ultra-dense neutron stars, or the final, cataclysmic collapse of a massive star into a black hole. These were one-shot wonders, the last screams of dying celestial objects. Then, in 2016, everything changed. The Arecibo Observatory in Puerto Rico detected an FRB coming from a dwarf galaxy 3 billion light-years away, and it did something extraordinary. It burst again. And then again. This object, designated FRB 121102, was the first known repeater. Its bursts were not periodic, They arrived in unpredictable clusters, sometimes remaining silent for months before firing off a frantic salvo of a dozen bursts in a single day. This simple fact repetition instantly annihilated the catastrophic one-off models. You cannot have a colliding star system or a dying star that explodes, then reassembles itself, and then explodes again in exactly the same way. The repeater demanded a completely new type of engine, one that could survive its own incredible outburst and reload for another. The sheer energy involved is what makes these objects so mind-bending. A single millisecond burst from a repeater can channel more energy than 500 million suns, all focused into a beam of coherent radio waves. This isn't a chaotic explosion. It's more like a cosmic laser pointer, incredibly focused and directed. To produce such a signal requires an environment of almost unimaginable ferocity, with immense magnetic fields and gravitational forces acting on a scale we can barely comprehend. The current best-fit explanation points to magnetars, those neutron stars with universe-breaking magnetic fields we encountered earlier. One model suggests that a magnetar's crust under titanic strain could crack in a starquake, releasing a blast of energy that shakes loose and accelerates plasma in its magnetosphere, creating a shockwave that produces the brilliant radio flash. Because the crust could fracture multiple times, this might explain the repeating nature. However, even this extreme model is pushed to its limits to account for the most energetic bursts we've recorded from these sources. The mystery deepens when we consider the patterns, or more accurately, the lack thereof. Some repeaters, like FRB 180916, discovered by the CHIME telescope in Canada, exhibit a periodic window of activity. It fires off bursts for roughly 4 days and then falls silent for 12, repeating this cycle every 16 days. This suggests the source is in an orbital system, perhaps with a companion star whose interactions periodically create the right conditions for bursting. Others show no rhyme or reason at all, their chatter appearing completely random. This has inevitably opened the door to more speculative ideas. Could we be witnessing the signature of immensely powerful interstellar beacons used for navigation by an advanced civilization? Or perhaps the exhaust plumes from light sails the size of planets, pushing spacecraft across the galactic voids. While these ideas reside firmly at the fringe of science, the repeated, engineered-looking nature of the signals forces astronomers to at least acknowledge that technosignatures must be ruled out before we can settle on a natural, albeit exotic, cause. The international effort to solve this puzzle is a testament to modern astronomy's global collaboration. From the massive 500-meter aperture spherical radio telescope in China to the deep space tracking networks of the European VLBI network, observatories around the world now engage in a frantic game of cosmic whack-a-mole. When a repeater fires, alerts are sent out instantly, and telescopes across the electromagnetic spectrum, optical, X-ray, gamma-ray, swing into action, hoping to catch any other signal associated with the event. This multi-messenger approach has already paid off. In 2020, observations linked an extremely powerful FRB from a magnetar within our own galaxy to a simultaneous X-ray burst, providing the first solid evidence that magnetars are indeed capable of producing at least some of these signals. Yet, even as we begin to pinpoint their sources, FRBs are proving to be useful tools in their own right. Each burst is an intergalactic messenger, carrying with it a hidden diary of its long journey. As the radio waves travel through the vast, diffuse gas that floats between galaxies, they are slightly slowed down, with lower frequencies arriving a fraction of a second after higher ones. This dispersion measure tells astronomers exactly how much material the signal has traveled through. By mapping the dispersion of countless FRBs, we are essentially creating a first-of-its-kind map of the otherwise invisible matter that weaves the cosmic web together, illuminating the missing normal matter that has long eluded our surveys. These mysterious flashes, born from unimaginable violence, are helping us chart the hidden architecture of the universe itself, turning a profound puzzle into a powerful new tool for cosmic cartography. And as we grapple with signals from across the cosmos, some of the most profound discoveries in the search for life are happening much closer to home, not on distant exoplanets, but right here in our own solar system, hidden beneath layers of ice on mysterious frozen moons. For centuries, we believed that a world needed to orbit within a star's Goldilocks zone, that narrow band where temperatures are just right for liquid water to exist, to have any hope of hosting life. But that entire concept has been turned on its head by a series of stunning discoveries from the outer solar system, revealing that some of the most water-rich, potentially habitable environments are not on planets at all, but on moons orbiting gas giants, kept warm not by sunlight, but by the relentless gravitational tug-of-war of their massive parents. These are the ocean worlds, and their existence has completely rewritten the rules of astrobiology. Our journey to these hidden seas begins with a small, cracked and crisscrossed moon of Jupiter, Europa. From afar, it looks like a celestial marble, its surface a smooth shell of water ice scarred by dark, rusty streaks. But the first hints that something extraordinary lay beneath came from the Voyager and Galileo spacecraft. They revealed a surface that is remarkably young and geologically active, with very few impact craters, suggesting something is constantly resurfacing it. The most compelling evidence, however, came from Galileo's magnetometer. As it flew by Europa, it detected something completely unexpected, an induced magnetic field. Jupiter's powerful magnetic field is constantly changing as it sweeps past Europa, and the Moon was generating a secondary magnetic field in response. The only plausible explanation for this is a global layer of electrically conductive fluid beneath the ice, and the best candidate for that by far is a salty, liquid water ocean. Current models suggest this ocean could be 60 to 100 miles deep, held in a liquid state by the immense tidal forces generated by Jupiter's gravity, which flex and heat the Moon's interior. This isn't a small, subsurface lake. It's a body of water holding potentially twice the volume of all of Earth's oceans combined, sloshing beneath an ice shell perhaps only 10 to 15 miles thick. But Europa is not alone in its secrets. At Saturn, the small, bright moon Enceladus presented an even more dramatic revelation. The Cassini spacecraft didn't have to infer the presence of an ocean, it flew right through it. Cassini's cameras captured stunning images of enormous plumes of water vapor and ice crystals erupting from a series of massive fissures near the Moon's south pole, like geysers shooting into space. On multiple daring passes, Cassini dove directly through these plumes, its instruments tasting their composition. The analysis was breathtaking. The plumes contained water vapor, salts, silica nanoparticles, and a variety of organic molecules including methane, carbon dioxide, and formaldehyde, the basic building blocks of chemistry. Most significantly, they detected a high concentration of molecular hydrogen. This is the chemical equivalent of finding smoke and knowing there must be a fire. On Earth, molecular hydrogen is a key energy source for microbes that live in hydrothermal vents at the bottom of our oceans. Its presence on Enceladus strongly suggests that on the seafloor of its hidden ocean, hot water is interacting with rock, providing not only the ingredients for life but also the energy to power it. Enceladus, a moon only 300 miles wide, has everything we know life needs: water, chemistry, and an energy source. Then there is Saturn's largest moon, Titan, a world so strange it feels like an entire planet. Titan is shrouded in a thick, orange haze with rivers, lakes, and seas dotting its surface. But these are not filled with water. On Titan's frigid surface, at minus 290 degrees Fahrenheit, the liquid is methane and ethane. It's a hydrocarbon paradise. For a long time, we assumed any water on Titan would be frozen solid into ice as hard as rock. but data from Cassini again appended our assumptions. Through precise measurements of Titan's gravitational field and its slight wobble in orbit, scientists found evidence for a liquid water ocean buried deep beneath the icy surface, perhaps 50 to 100 miles down. This is a different kind of ocean world, one sandwiched between a rocky core and a thick icy shell, with its own alien landscape of methane lakes above it. This raises an incredible possibility. Could Titan have two separate, non-mixing liquid environments capable of hosting life? The surface hydrocarbon lakes and the subsurface water ocean. Life in the subsurface ocean might resemble what we theorize for Europa or Enceladus, but some astrobiologists speculate about a truly alien form of life in the surface lakes, one that uses liquid methane instead of water as its solvent, a concept that stretches our definition of biology to its absolute limit. The implications of these discoveries are nothing short of revolutionary. We now know that liquid water, the one universal prerequisite for life as we understand it, is not a rare commodity limited to the inner solar system. It appears to be common in the frozen outskirts, kept liquid by a process we now understand, tidal heating. The gravitational pull from a giant planet stretches and squeezes its moons, generating internal friction and heat. This means that anywhere you have a moon with a somewhat eccentric orbit around a gas giant, you have the potential for a subsurface ocean. This vastly expands the number of potential habitats in our galaxy alone, suggesting that life could be flourishing in the dark under ice around countless stars. This new understanding has directly fueled an ambitious new era of solar system exploration. NASA Europa Clipper mission, scheduled to launch in October of this 2024, is designed to conduct dozens of close flybys of Europa, using a powerful suite of instruments to precisely measure the thickness of its ice shell, the depth and salinity of its ocean, and to analyze the composition of its surface material and any plumes it might sniff out. Even more dramatically, the agency is already planning for a Europa lander, a mission that would touch down on the icy surface and potentially drill or melt its way through the ice to directly sample the ocean below. Meanwhile, several concepts are being studied to return to Enceladus, perhaps with a dedicated orbiter and a lander that could analyze the fresh material falling back to the surface from its plumes, or even a drone that could fly through the geysers themselves. These are not merely missions of discovery, they are missions with the explicit goal of determining whether we are alone in the universe by going to the places in our own celestial backyard that are most likely to provide an answer. The ocean worlds have transformed our search for life from a theoretical exercise focused on distant points of light into a tangible, solar system-wide quest, promising that the first discovery of extraterrestrial life may not be in a galaxy far, far away, but right next door, waiting beneath the ice. After journeying from the heart of our solar system to the farthest edges of the observable universe, we arrive at a final mystery that is arguably the most profound of all, because it doesn't concern a single strange object, but threatens to unravel our entire understanding of cosmic physics itself. This is the Hubble tension, a stubborn and growing discrepancy that has split the field of cosmology into a genuine crisis, revealing that our most precise measurements of the universe's expansion are fundamentally, and perhaps wonderfully, at odds. The story begins with a simple question: how fast is the universe expanding? The answer is encapsulated in the Hubble constant, a number that represents the rate at which galaxies are receding from us for every megaparsec of distance. For decades, astronomers have pursued two primary, independent methods to pin down this critical value. The first approach is to build a distance ladder within the local universe. This meticulous process starts with precise parallax measurements to nearby stars, uses those to calibrate the distance to variable stars called Cepheids in our galaxy, and then uses those Cepheids to calibrate the distance to even brighter supernova in other galaxies. By measuring how fast those distant galaxies are moving away from us and dividing by their independently measured distance, you get the Hubble constant. This local method, championed by teams like the one led by Nobel laureate Adam Rees, has been refined to an astonishing degree of precision, most recently using the Hubble Space Telescope itself. Their result is a very specific number, approximately 73 kilometers per second per megaparsec. The second method takes a completely different approach, looking not at the nearby universe but at its very first light. This involves studying the cosmic microwave background, the faint afterglow of the Big Bang, as exquisitely mapped by the Planck satellite. The tiny temperature fluctuations in this ancient light are a frozen baby picture of the infant universe, encoding a wealth of information about its composition and geometry. By plugging these observations into our standard model of cosmology, known as lambda cold dark matter, we can run the cosmic film forward 13.8 billion years to predict what the Hubble constant should be today. This early universe method yields an equally precise but starkly different result, around 67 kilometers per second per megaparsec. The problem is that these two numbers, each derived from impeccable data and methods, do not agree. The gap between them is not a minor statistical fluke. It is a discrepancy of over 4.5 sigma, meaning there is only a 1 in 100,000 chance that it's a random error. This is the Hubble tension. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths every single time. One ruler, built from the local universe, tells us the cosmos is expanding at one speed. The other ruler, built from the primordial universe, insists it must be expanding slower. Both cannot be right. This isn't just a small accounting error. It is a direct challenge to the bedrock of modern cosmology, suggesting that something in our standard model is either incomplete or fundamentally wrong. The implications of this unresolved tension are monumental. It forces us to confront the possibility that we need new physics beyond our current understanding. Perhaps dark energy, the mysterious force driving the acceleration, is not a constant as Einstein proposed, but a dynamic field that has evolved over time, growing stronger or weaker in a way we haven't accounted for. Or maybe dark matter has properties we haven't yet discovered. Perhaps it can interact with itself or with light in a subtle way that changes how structures formed. Another compelling, though more exotic, idea is that our universe is not perfectly uniform on the largest scales. We operate on the cosmological principle, which assumes the universe is homogeneous and isotropic, the same everywhere. But what if we live in a local under-dense region, a giant cosmic void? This could mean our local measurements of the expansion rate are artificially high, not representative of the true global average, like being in a valley and misjudging the height of the surrounding mountains. Resolving this crisis is the primary goal for a new generation of observatories. The James Webb Space Telescope is now scrutinizing the same Cepheid variables and supernova as Hubble, checking for any hidden systematic errors in the local distance ladder with its superior infrared vision. Meanwhile, projects like the Vera C. Rubin Observatory will map the universe in unprecedented detail, using techniques like gravitational lensing and the distribution of galaxies to provide entirely new, independent measurements of the expansion rate. Each new dataset is a crucial piece of the puzzle, either deepening the tension and confirming the need for revolutionary physics, or finally identifying a hidden flaw in our methods. The beautiful and somewhat terrifying prospect is that the Hubble tension may not have a simple solution. It might be the first undeniable crack in our standard model, a signal from the cosmos that there are deeper layers of reality we have yet to uncover. Just as past discrepancies led to the discoveries of dark matter and dark energy, solving this crisis could open the door to a new chapter in physics, revealing something entirely unexpected about the fundamental nature of time, space, and energy. It is a humbling reminder that for all our knowledge, the universe still holds its greatest secrets close, waiting for that next moment of brilliant insight to show us the way. From the baffling precision of Saturn's hexagon to the silent hurricane of dark matter passing through us at this very moment, our journey through the cosmos has revealed a universe far stranger and more wonderful than we could have ever imagined. We've stood in awe of stellar vampires and zombie stars that defy death, wrestled with the invisible pull of the great attractor, and felt the chilling possibility that our entire reality might bear the scar of a collision with another universe. Each of these 30 discoveries, from the planetary to the galactic to the universal scale, is a powerful testament to one simple, profound truth. The universe is not only weirder than we imagine, it is weirder than we can imagine. Yet, this incredible strangeness is not a barrier to understanding. It is the very engine of scientific progress. Every anomaly, every discrepancy like the Hubble tension, every signal that doesn't fit is not a failure of our models but a gift. It is a flashing signpost pointing toward the next great breakthrough, the next revolution in physics, the next leap in our comprehension of reality itself. These mysteries are the frontiers of human knowledge, and it is at the frontier where the most exciting discoveries are always made. They remind us that science is not a static set of facts in a textbook, but a living, breathing, and dynamically evolving conversation with the cosmos, a conversation where the universe often has the most surprising things to say. So as we conclude this tour of the inexplicable and the sublime, let it serve not as a final answer, but as an invitation to remain curious, to look up at the night sky with a sense of wonder, and to embrace the beautiful fact that we live in a reality still brimming with secrets waiting to be uncovered. The greatest discoveries are still out there, hidden in the data, lurking in the darkness between the stars, or perhaps right here in our own solar system, waiting for the next curious mind to find them. Now, we want to hear from you. Which of these cosmic mysteries captured your imagination the most? Was it the silent enigma of Oumuamua, the terrifying power of a magnetar, or the hidden oceans of Europa? Let us know your favorite in the comments below, and be sure to subscribe and hit the notification bell so you don't miss our next journey into the depths of space, time, and mystery. The universe is vast, strange, and full of stories. Stay curious and let